Introduction. This is a certification-grade course on agentic AI coding, and it is built for one specific person. You have 10 or more years in software. You have shipped systems and then maintained them, which is the harder half. And you have done essentially nothing with AI tooling. You do not know what a token is, or a harness, or MCP. You are not behind on engineering. You are behind on one vocabulary and one set of tools. 4 ground rules, and I will hold myself to them out loud. First, every load-bearing claim traces to a named source, spoken with its date, so you can go and check it. Where I am reasoning rather than reporting, I will say so. Second, the research behind this course is current to August 2026. That matters more here than in almost any field, because the ground moved recently, and confident material written 18 months ago is now wrong in specific, checkable ways. Third, where something is uncertain or contested, I will say so rather than smooth it over. One rigorous study cuts directly against the enthusiasm, and it gets a full chapter rather than a footnote. Fourth, I am not selling you anything. No vendor commissioned this. Where a vendor's own documentation is the best available source, I will cite it and name the incentive in the same breath. This is part 1 of a series. Part 1 is foundations, the vocabulary, and the mental model. Part 2 is the comparative landscape of actual tools. Part 3 is engineering judgment at scale. The promise is narrow, and I think it is achievable. By the end of Part 1, you will not merely recognize these words. You will be able to make decisions with them. Chapter 1, The Engineer Who Missed 5 Years. Start with the reassurance, because you have earned it and because it happens to be true. You did not miss 5 years of software engineering. You missed 5 years of one specific vocabulary and one specific set of tools. Those are different things, and that difference is most of this chapter. Here is what still applies, entirely unchanged. Decomposition, interface design, knowing when a change wants a migration and when it wants a feature flag, testing strategy, and the judgment about which tests are actually worth having. Code review, both the reading of a diff and the social craft of giving feedback on one. Observability, on call, the discipline of a blameless postmortem. Idempotency, knowing what done means for a given change and refusing to say it before it is true. Every one of those transfers intact. None of it is obsolete. If anything, the scarce resources have moved toward exactly the things you are already good at. That last claim is not originally mine. Simon Willison, co-creator of Django and one of the most careful chroniclers of this field, publishing near-daily notes on it since 2022, frames it this way in his Agentic Engineering Patterns Guide of February 2026. Writing code is cheap now. The cost of producing initial working code has fallen close to nothing. What remains scarce is review, verification, and judgment. If that framing is right, and I think it is, then a 10-year engineer is not behind. A 10-year engineer is holding most of what is left. So what do you actually lack? 2 things. The first is a vocabulary, tokens, context windows, context engineering, harness, agent loop, tool use, the model context protocol, which everyone calls MCP skills, subagents, permission modes, evals, roughly 40 terms, most of them coined between 2023 and 2026, several of them still genuinely contested. I will define every one of them from nothing, the first time it appears, and I will tell you which are settled terminology and which are somebody's blog post that happened to catch on. The second is a set of tools, and more importantly, the operating discipline that makes them useful. That discipline is not obvious, and it is not the same as installing an editor plugin. Now the reframe. This is the single most valuable sentence in the chapter, and I want you to carry it through the entire course. Birgitta Bokeler and her colleagues at ThoughtWorks have been keeping a long-running field record called Exploring Generative AI, published on martinfowler.com. Their one-line correction to the mental model an engineer arrives with is this, and I am quoting it exactly. The thing they call an LLM is a large language model, the component underneath all of these tools, and Chapter 3 takes it apart properly. LLMs are not compilers, interpreters, transpilers, or assemblers of natural language. They are inferers. Sit with that because it is doing a lot of work. You have spent a career surrounded by translators. A compiler takes source and produces bytecode. A transpiler takes one language and produces another. A code generator takes a schema and produces a client. Every one of those has three properties you rely on without noticing. It is deterministic, so the same input gives the same output. It is total in a useful sense, meaning it either succeeds or it fails, and there is no third state. And crucially, it has an accept and reject boundary. If the compiler accepts your program, that acceptance means something definite. If it rejects it, you get a location and a reason. An inferer has none of that structure. You give it a description of what you want, and it produces the most plausible continuation given everything it has seen. There is no accept step. There is no reject step. There is no error channel. Nothing anywhere in that pipeline evaluates whether the output is correct. Plausibility is the only property the machine is optimizing, and plausible and correct are correlated without being the same thing. 3 consequences follow, and they are the whole reason your supervision has to change shape. The first is that the same input can produce different output. Run the same request twice, and you can get 2 different implementations, both reasonable. That is not a bug, and it is not a fault in your prompt. It falls directly out of how the output is produced, which is the subject of Chapter 3. The second is that failure looks like success. This is the one that gets experienced engineers. A compiler that fails hands you a stack trace. An inferer that fails hands you a confident, well-structured, correctly indented near miss. It compiles. It reads well. The variable names are good. And the thing it is doing is subtly not the thing you asked for. You do not have to take my word for how common that is. The Stack Overflow Developer Survey of 2025, with around 49,000 respondents, found that the single most cited frustration, named by 66% of developers, was AI solutions that are almost right, but not quite. 45.2% said debugging AI-generated code takes more time than writing the code by hand would have. That is the inferer property showing up as a survey result. The same survey is worth one more moment because it describes the situation you are walking into. 84% of developers use or plan to use these tools, up from 76% the year before. 51% of professionals use them daily. And yet only 3.1% say they highly trust the accuracy of the output, while 45.7% actively distrust it. Positive sentiment fell from over 70% to 60%. Near universal adoption alongside low and falling trust is not a contradiction. It is the signature of a tool that is genuinely useful and genuinely unreliable. Which is, I would argue, precisely the category of thing engineering discipline was invented to manage. You have managed unreliable but useful components before. Networks. Third-party APIs. Hardware. Junior engineers, including yourself once, you know how this is done. You wrap it in checks. The third consequence is the practical one. Because there is no accept-reject boundary in the machine, you have to supply one from outside. Anthropic's own engineering documentation puts it about as bluntly as it can be put. Claude stops when the work looks done. Without a check it can run, looks done is the only signal available, and you become the verification loop. Read that again as a design constraint rather than a tip. If the agent has no test suite to run, no build that can fail, no linter, no type checker, no fixture to diff against, then the only termination signal available to it is its own impression that the output resembles a finished thing. And you, personally, become the only real verifier, at the speed of human reading, for output produced at machine speed. That trade goes badly. So here is the one thing to take from this chapter and act on immediately before you have learned a single new term. Before you hand any task to any of these tools, decide what evidence of completion you are going to demand and make sure it is evidence a machine can produce. Test output, an exit code, a diff against a known good fixture. not an assertion from the model that it has finished. The ThoughtWorks group frames the same disciplines slightly differently as a continuous risk assessment. For each piece of work, weigh the probability that the AI gets it wrong against the impact if it does. Low probability and low impact, let it run. High impact, put a gate in front of it. That is the reframe. You are not learning to trust a new compiler. You are learning to supervise a fast, well-read, entirely stakeless collaborator that will never tell you it is unsure. Everything else in this course is machinery for doing that well. Here is the shape of what is coming. Chapter 2 is the dated evidence that something genuinely changed, and when. Chapter 3 gives you the minimum accurate model of the machine itself. Chapters 4 and 5 are about context, which is where most real failures actually live. Chapters 6 through 9 build up from workflows to agents to the harness that surrounds them. Chapters 10 through 14 cover the extension points you will actually configure: MCP, skills, memory files, subagents, permissions, and sandboxes. Then we turn critical. Vibe coding versus agentic engineering, what the evidence honestly says, security, and why benchmark scores mislead. We finish with a concrete first week and a verdict I will tell you how to falsify. One last thing about the title of this chapter. You did not miss a slow 5-year drift. Most of the vocabulary accumulated gradually, yes, but the capability change that makes any of this worth your attention is dated by 2 independent observers to a specific 2-month window at the end of 2025. That is a strong claim, and it needs evidence. That is Chapter 2. Chapter 2, what actually changed. If you take one factual claim away from this entire course, take this one. 2 credible, independent observers, working from different vantage points and different evidence, both date a real step change in coding agent capability to the same narrow window, November and December of 2025. That is the spine of everything that follows. It is also the explanation for the odd position you are in. It is not that you were inattentive. It is that the thing worth paying attention to is genuinely recent, and a great deal of the confident writing about coding agents predates it and is now describing a different set of tools. Let me give you the evidence properly, because a dated claim is only as good as its sources, and then let me tell you exactly how much weight it can bear. That second part matters more than the first. Start with Andrej Karpathy, because his testimony carries unusual weight for a specific structural reason. Karpathy was a founding member of OpenAI. He was senior director of AI at Tesla, where he led the Autopilot Vision team. He created Stanford's CS231N, which is the course a great many practicing machine learning engineers actually learned from. He now runs Eureka Labs. He is also the most consequential namer in this field. He coined Software 2.0, and he coined the term vibe coding, which we will come back to in a later chapter because he has since drawn a careful line around it. Here is the structural point. Karpathy does not sell a coding agent. He has no product whose revenue depends on you believing agents work. That is precisely why the rest of the industry treats his position changes as signal rather than marketing, and it is why I am spending this much of the chapter on one person. Now the sequence with dates. In June 2025, speaking at Y Combinator's AI Startup School in San Francisco, Karpathy gave a talk called "Software is Changing Again?" In it he said, deliberately and against the industry slogan of the moment, "This is the decade of agents." Read that as the deflationary claim it was. Everyone else was saying 2025 is the year of agents. He was saying, no, this is a 10-year problem. From the same talk, a line worth keeping for its own sake. Demo is works.any, product is works.all. Then October 2025. Karpathy appeared on the Dwarkesh Patel podcast, and his position there was clearly skeptical. His argument, and I am paraphrasing his reasoning rather than quoting it, was that agents were cognitively inadequate for real work, not enough multimodality, no working long-term memory, no continual learning. Unable to reliably operate a computer over a long horizon. He is widely reported as summarizing this in 3 blunt words: they just don't work. I want to flag that the 3-word version is reported by several outlets, but was not verified against the podcast transcript in the research behind this course. Treat the exact phrasing as secondhand. The substance of his skepticism is not in doubt. Now February 2026. 4 months later, Karpathy publicly reversed. Simon Willison quoted him in full with a link on the 26th of February 2026. Here is the quote. "I have expanded one abbreviation so it reads aloud, nothing else is changed." It is hard to communicate how much programming has changed due to AI in the last 2 months. Not gradually and over time in the progress as usual way, but specifically this last December. There are a number of asterisks, but, in my opinion, coding agents basically didn't work before December and basically work since. The models have significantly higher quality, long-term coherence and tenacity, and they can power through large and long tasks, well past enough that it is extremely disruptive to the default programming workflow. Notice what kind of claim that is. It is not, the models got a bit better. It is a claim about a discontinuity with a month attached from someone who was on record 4 months earlier saying the opposite. People do not usually publish that. Now the second observer, and the reason this chapter exists rather than being one man's anecdote. Simon Willison co-created Django. He built Dataset and the LLM command line tool. He has been publishing near-daily notes on this field since 2022, with over 345 posts under his AI-assisted programming tag alone. He links and quotes primary sources compulsively. No model vendor employs him. If Karpathy is the field's most consequential namer, Willison is its most reliable running record. Willison did not respond to Karpathy. He got there first, independently, and he built it into the structure of his own blog. He has a tag, a permanent category, literally named November 2025 inflection. His own description of that tag, verbatim. November 2025 felt like an inflection point for coding agents, with Opus 4.5 and GPT 5.1 and GPT 5.1 codecs, increasing the utility of those agents in a very noticeable way. And on the 4th of January 2026, again verbatim. It genuinely feels to me like GPT 5.2 and Opus 4.5 in November represent an inflection point, one of those moments where the models get incrementally better in a way that tips across an invisible capability line, where suddenly a whole bunch of much harder coding problems open up. 2 people, different jobs, different evidence, different writing venues, no coordination, one of them publicly contradicting his own position of 4 months earlier. Same window. There is a small discrepancy worth naming rather than papering over. Willison says November and points at specific model releases. Karpathy says December. My reading, and I am labeling this as my inference rather than a documented finding, is that the releases landed in November and the felt effect in day-to-day work arrived a few weeks behind them, which is what you would expect when the change is in how far a tool gets before it needs you. But the honest version is, they name the same 2-month window and they do not agree on the month. So what specifically is supposed to have improved? Both accounts point at the same 3 properties, and they are worth translating out of the vocabulary. Long-term coherence means the agent still knows what it is doing on step 40. Earlier tools would start a refactor competently, and several files in, quietly lose the thread, contradict a decision they had made 20 minutes earlier, or reintroduce a bug they had just fixed. Tenacity means it keeps going. This one is easy to underrate. A tool that stops at the first ambiguity or declares success the moment the output superficially resembles a finished thing is a tool you have to babysit turn by turn. A tool that hits a failing test, reads the failure, forms a hypothesis, changes something and runs the test again is a categorically different thing to supervise, even if the underlying model is only somewhat better. And powering through large, long tasks is the consequence of the first 2. It is the difference between a tool that helps you write a function and a tool you can hand a multi-file change to. Willison's phrasing is that a whole class of much harder problems opens up. Now the part I care most about, which is how much weight this can bear. This is practitioner testimony. It is not a controlled study. 2 observers is 2 observers, however credible, and both of them are enthusiasts in a field with enormous financial energy behind it, even though neither works for a model vendor. Self-report about AI productivity has a specific, measured, documented failure mode, and I am not going to hide it from you in the chapter where I am telling you things got better. In July 2025, the research organization METR published a randomized controlled trial. 16 experienced developers, working on large mature open-source repositories they knew well, completing 246 real issues. The headline finding, verbatim: when developers are allowed to use AI tools, they take 19% longer to complete issues. And the part that should stop you cold, those developers expected to be sped up by 24%, and after being slowed down by 19%, they still believed they had been sped up by 20%. That is the strongest evidence in the field that practitioners cannot feel their own productivity accurately. It applies to Karpathy and Willison too, and it applies to me. 2 things must be said about it, and both are true at once. The first is that the study tested tooling from early 2025, primarily Cursor Pro with Claude 3.5 and 3.7 Sonnet, which is squarely pre-inflection. Applying it directly to today's tools is not fair to the tools. The second is that no equally rigorous post-inflection randomized trial has been identified as of August 2026. Not one that contradicts METR, and not one that confirms the practitioner accounts either. So the honest position is that the best controlled evidence we have is about a previous generation of tools, and the evidence about the current generation is testimony. Hold both. That is the intellectual posture of this entire course. Chapter 16 takes the evidence apart properly. What you can act on now is this. Anything you read about coding agents dated before roughly November 2025, including the skeptical material and including the enthusiastic material, is describing a different generation of tool, and you should check the date before you weight the claim. That single habit will save you from most of the confusion in this space. Next, the machine itself. Before we can talk about what agents do well, you need an accurate and entirely unmystical model of what is underneath them. Chapter 3: Tokens, Weights, and the Machine. You do not need transformer mathematics to use these tools well. You do need enough of a model to predict how they fail. You never wrote a TCP stack either, but you know packets can arrive out of order, and that is why your retry logic is not naive. So this chapter is the minimum accurate mental model. 4 ideas: tokens, next token prediction, the split between training and inference, and the sampling on top. Then 2 terms you will meet constantly: system prompts and open versus closed weights. No brain analogies. Nothing here is mysterious. Start with tokens, because everything is priced, budgeted, and degraded in them. A token is not a word, and it is not a character. It is a chunk of text produced by a tokenizer, a lookup table built before training that maps text fragments to integers from a fixed vocabulary. A common English word is usually 1 token. A rare word breaks into 2 or 3. An unusual identifier in your codebase might be 5. Whitespace and punctuation cost tokens. A block of JSON costs more than the same information as prose, because the braces and quotes are tokens too. The model never sees your text. It sees a sequence of integers. 2 consequences you will feel immediately. Tokens are the billing unit, so cost tracks text volume, not task difficulty. And tokens are the budget unit for the context window, the model's working set, which gets the next chapter to itself. Here is how mechanical this is. As of August 2026, Anthropic's own pricing documentation notes that models from Opus 4.7 onward use a new tokenizer, producing roughly 30% more tokens for the same text than the previous one. Same words, same information, 30% more tokens, therefore more cost and more context consumed. Cost comparisons across that boundary are invalid. So token count is not a property of your text. It is a property of the tokenizer attached to whichever model you are using. Anyone quoting a per-task token cost without naming the model is quoting you nothing. Now the core mechanism, and it really is this simple to state. The model takes a sequence of tokens and produces a probability distribution over what the next token should be. Something picks one. That token is appended and the whole thing runs again. That is the entire operation. Everything else, chat, tool calls, reasoning agents, is scaffolding on that loop. Take the case engineers find most surprising: tool use. When an agent runs your test suite, the model did not run anything. It emitted tokens forming a structured block, naming a tool and its arguments. Anthropic's own documentation puts it plainly: the model returns a structured call that your application executes. Your harness, the program wrapped around the model, parses that block, runs the command, and feeds the result back as more tokens. A text predictor and ordinary software acting on its output. Chapter 8 does this properly. Third idea: training versus inference. This is where most naive expectations break. Training produced the weights, the numerical parameters of the model, some very large number of them. It is an enormous offline computation someone else ran. Inference is what happens when you send a request. The weights are loaded, your tokens go in, predicted tokens come out. At inference time, the weights are frozen. Nothing you do in a session alters the model. It does not learn from your code base. It does not learn from your correction. It does not remember you tomorrow. Weights change only when someone deliberately runs a training job, which is an offline engineering project, never a side effect of a conversation. Two practical things fall out of that. The first is the knowledge cutoff. Every model's world knowledge stops at the date its training data stopped, and those dates do not track capability the way you would assume. As of August 2026, in Anthropic's own model documentation, Opus 5 carries a knowledge cutoff of May 2026, while Fable 5, positioned above it in capability, has a cutoff of January 2026. The more capable model knows less recent things. So, use the best model, it will know about the library I just adopted, is not a safe inference. It may be confidently describing an API as it stood 18 months ago. The second consequence is statelessness. If the model does not remember, everything it knows about your current work has to be resent on every call. That is exactly what happens. From the Claude Code documentation, verbatim. Claude Code sends your full conversation with every request, and each time Claude uses tools, it sends another request carrying that batch of tool results. Every turn is a fresh, amnesiac request that happens to include a transcript. What feels like memory is your harness rereading files from disk and re-injecting them. What feels like the agent learning your conventions is a file being pasted back in every time. That one fact explains a great deal of otherwise inexplicable behavior, and it is why the discipline that matters is called context engineering. Fourth, why models hallucinate. You now have enough machinery to see it, and I want to kill the moral framing. A hallucination is not a lie. Lying requires a model of the truth plus an intent to misstate it. The machine has neither. It is producing the most plausible continuation of a token sequence, and plausibility is not truth. The two correlate strongly, because plausible text is usually true text, which is why any of this works at all, but nothing in the mechanism checks. There is no step at which the system asks whether what it is emitting corresponds to reality. A function name that looks exactly like a function name in that library is a good prediction, whether or not it exists. The best documented case makes the mechanism visible. A team led by Spracklin, presenting at USENIX Security 2025, studied package hallucination, meaning cases where a model imports a library that does not exist. They found roughly 205,000 unique hallucinated package names. Then the detail that should change how you think about this. They reran prompts that had produced a hallucinated name 10 times each. 43% of the hallucinations recurred on every single run. 58% appeared in more than one run. Hallucinations are not random noise. The same plausible-looking wrong answer comes back reliably because it is the same distribution being sampled from the same frozen weights. That repeatability is what makes it a security problem rather than a nuisance, which is Chapter 17's business. As a mechanism lesson, wrong output is not the machine glitching. It is the machine working exactly as designed, on a question where plausible and correct diverged. This does not go away with better models. A 2026 follow-up on the current frontier cohort measured package hallucination rates between roughly 4.6 and 6.1%, 3 to 4 times better, with a floor still several percent. At the volume an agent installs dependencies, that is not a small number. Now the knobs. The model produces a distribution over the next token, and something has to pick one. Greedy decoding always takes the highest probability token. Sampling draws from the distribution, so lower probability tokens sometimes win. Temperature controls the shape. Low temperature sharpens it toward the favorite and makes output more repetitive. High temperature flattens it and makes output more varied. Two related knobs, top K and top P, truncate the candidate set before sampling. This is why the same prompt run twice can produce two different implementations. Not instability. Sampling. My opinion, labeled as opinion, in agentic coding you will almost never touch these. The harness sets them, and your leverage is in context and verification. One grounded caution, because it generalizes. Point a tool at a third-party endpoint, and your sampling parameters are not guaranteed to be honored. DeepSeek's Anthropic-compatible API, in its own official documentation, states that it ignores several parameters including top K. It does not error. It ignores them. A knob that is silently discarded is worse than a knob that is missing, and that pattern recurs across this ecosystem. 2 pieces of vocabulary, and we are done. A system prompt is text placed at the front of every request that frames the model's role, describes its tools, and states its rules. In a coding harness, you usually do not write it. The vendor ships it, and it is often substantial. It is also not free. Tool definitions are input tokens on every request, plus a hidden tool use system prompt on top. Anthropic publishes per model counts. For example, 286 tokens for Claude Opus 5 when tool choice is set to automatic. 20 tools you never call still cost you tokens every turn. 2 warnings, both grounded. A system prompt is not a security boundary. System prompt leakage is item 7 on the OWASP Top 10 for LLM applications, the 2025 edition, which is the standard taxonomy for this class of risk. Do not put a secret in one, and its instructions are advisory, not enforced. The Claude Code documentation is unusually honest here. Project instruction files are delivered as a user message after the system prompt, not as part of the system prompt itself. Claude reads it and tries to follow it, but there's no guarantee of strict compliance. If you need a guarantee, you need a mechanical block, not a sentence. Chapters 12 and 14 build on that. Finally, open weight versus closed, definitionally only. An open weight model is one whose trained parameters are published, so you can download the checkpoint and run it on infrastructure you control. A closed model is available only through an API. There is no checkpoint. 3 cautions. Open weight is not the same as open source, and licenses here range from MIT and Apache 2.0 through to bespoke terms with revenue triggers. Essentially, none of these models publish their training data, so even a permissive checkpoint is not a reproducible artifact. And the license belongs to the release, not the lab, so you check it per model every time. Part 2 covers who is competitive and when self-hosting pays. That is the machine. A tokenizer, a frozen pile of weights, a next token distribution, a sampler, and an ordinary program around it doing all the acting. Everything it knows about your problem has to arrive through a window of tokens on every call. That makes the window the scarcest resource you manage, and it behaves nothing like the filing cabinet you are picturing. Chapter 4. Chapter 4. The context window is not a filing cabinet. Here is what almost every experienced engineer does the first time they sit down with a coding agent. They look up the model's advertised context window. 200,000 tokens, 1,000,000 tokens, whatever the number happens to be that month. Then they look at their repository, do a rough division in their head, and think, I could just put the whole thing in there. I want to spend a chapter on why that instinct is wrong, because it is the single most productive misconception to clear out early. Almost everything else in this course is downstream of it. Start with what a context window actually is. A token is the unit the model operates on, a chunk of text roughly the size of a word fragment. The context window is the maximum number of tokens the model can have in front of it during a single forward pass. And that budget is not just your question. It is the system prompt the tool ships with, the definitions of every tool the model is allowed to call, every file it has read, the output of every command it has run, and every word it has already said back to you. All of it summed on every call. Now the part that surprises people with a system's background. In an agent loop, the entire conversation is resent on every single request. The model holds no state between calls. The Claude Code documentation says it plainly. Claude Code sends your full conversation with every request, and each time Claude uses tools, it sends another request carrying that batch of tool results. So context is a cumulative cost, not an incremental one. Every file you dump in is paid for again on turn 2, and turn 3, and turn 40. That is the billing argument, and it is real. But it is the weaker of the two arguments. The stronger one is that stuffing the window makes the model measurably worse at its job. Anthropic's engineering team stated it in one sentence in their post on context engineering, published in September 2025. Verbatim, as the number of tokens in the context window increases, the model's ability to accurately recall information from that context decreases. The phenomenon has a name in the field. It is called context rot. Notice what it is not. It is not the model running out of room. It is the information you put in early becoming less reliably retrievable the more you pile on top of it. You deserve the mechanism rather than an assurance, so here it is. The architecture underneath all of these models is the transformer, and the defining operation of a transformer is attention. Every token in the context is compared against every other token in the context. Anthropic's post spells out the consequence. Transformers require, quote, every token to attend to every other token across the entire context, producing, quote, n-squared pairwise relationships for n tokens. Sit with that scaling for a second, because it is the whole chapter. Double the context, and you quadruple the pairwise relationships the model has to distribute its attention across. The model has a finite attention capacity trained into it, and you are spreading that same capacity thinner over a much larger set of relationships. Which is why the filing cabinet is the wrong picture. In a filing cabinet, a document you filed on Monday sits there, inert and undamaged, until you go and pull it out. Nothing degrades because you added more folders. The context window does not work like that. A closer analogy from ordinary engineering life is a code review. A reviewer holding 200 lines in their head can genuinely reason about how line 12 interacts with line 190. Hand the same reviewer 4,000 lines, and the failure is not that they run out of desk space. It is that the quality of every individual judgment quietly drops, including judgments about the lines they were previously handling fine. The term context rot was popularized by a technical report from a company called Chroma, titled Context Rot: How Increasing Input Tokens Impacts LLM Performance, by Kelly Hong, Anton Troinikov, and Jeff Huber, published on the 14th of July, 2025. Their framing, verbatim. Large language models are typically presumed to process context uniformly. That is, the model should handle the 10,000th token just as reliably as the 100th. However, in practice, this assumption does not hold. As reported, all 18 frontier models they tested degraded as input length increased, including on tasks as trivial as retrieval and copying text back out. I should be honest that I have the details of that report from summaries rather than from a full reading of it, so treat the specifics as well supported rather than nailed down. And I want to name an incentive because the discipline of this course requires it. Chroma sells a vector database. A company selling retrieval infrastructure has an obvious commercial interest in the conclusion that long context is not a substitute for retrieval. That does not make the finding false. What makes me believe it is that Anthropic uses the same term and reports the same effect in its own engineering writing, and Anthropic sells the long context windows. When two parties with opposing commercial incentives independently describe the same limitation, believe them. There is a related, older, well-documented effect worth carrying with you. Models attend far better to the beginning and the end of their context than to the middle. It is known as lost in the middle. The practical translation is that the crucial constraint you buried in paragraph 9 of a very long prompt is the single most likely thing to be ignored. You will hear specific rules of thumb circulating about how much of an advertised window is actually usable at high accuracy. I could not verify any of those numbers against a primary source, so I am not going to repeat them. Treat them as folklore. The shape of the claim is well established. The digits are not. So here is the conclusion, stated as an engineering fact rather than a slogan. Context is a finite resource with diminishing marginal returns, and a bigger window does not straightforwardly solve the problem, because a bigger window raises the ceiling without improving the quality of attention underneath it. In fact, I would argue a bigger window makes the problem harder to notice, because the degradation arrives later and more gradually rather than announcing itself as a hard error. That last point is my inference from the evidence, not a documented finding, so hold it loosely. Now, the useful thing about this claim is that it shows up independently from the practitioner side. The Claude Code Best Practices documentation says that most of its recommendations derive from a single fact, near verbatim. Claude's context window fills up fast, and performance degrades as it fills. It goes on to describe the context window as, quote, the most important resource to manage. That is two documents, one written from research and one written from daily practice, arriving at the same constraint. That convergence is why I am comfortable teaching it as settled. Which brings us to the standard response and the first real technique in this course. It is called compaction. Anthropic's definition, verbatim, compaction is taking a conversation nearing the context window limit, summarizing its contents, and reinitiating a new context window with the summary. Read that carefully and you will see the trade immediately. You gain room, you lose fidelity. A summary is lossy by construction, and you do not get to choose in advance which detail gets dropped. Two consequences you should know before you ever meet the feature. First, compaction is itself an expensive operation, because summarizing a conversation means reading the whole conversation you are summarizing. If you do not actually need continuity, clearing the session outright is free and is usually the right move. Second, and more serious, compaction can silently drop your constraints. The Claude Code permission documentation warns that a boundary you stated in conversation, something like, do not push until I have reviewed it, can be lost if compaction removes the message that stated it. That is worth sitting with, because it is the first appearance of a theme this course will return to repeatedly. A rule you said out loud is a suggestion with a good hit rate. A rule enforced by a mechanism is a guarantee. They are not the same thing, and the difference is invisible right up until it matters. Here is what you can do with this on Monday morning. Treat the context window as a budget you are spending, not a container you are filling. Give the agent the 3 files that matter rather than the 30 that might. Start a fresh session when the task changes rather than letting one conversation sprawl across 4 unrelated problems. And when you catch yourself saying, "It forgot what I told it," stop and recognize what you are actually looking at. That is almost never a model failure. It is a context failure, and it is yours to manage. Managing that budget deliberately, turn after turn, across a long agent run is not an ad hoc habit. It is a discipline with a name, a definition, and a small set of named techniques. That is the next chapter. Chapter 5, From Prompt Engineering to Context Engineering. For about 3 years, roughly 2022 through 2024, the skill everyone talked about was prompt engineering. There were courses in it. There were job postings for it. There was a genre of blog post consisting of clever phrasings that supposedly made the model try harder. Some of it was real craft. A lot of it was superstition. That skill has not disappeared, but it has been demoted. It is now a subset of something larger, and if you learn the larger thing, you will not need most of the tricks. Here is the definition, and I am going to quote it exactly because the precision matters. Anthropic's applied AI team, in an engineering post published on the 29th of September 2025, define context engineering as, quote, the set of strategies for curating and maintaining the optimal set of tokens, information, during LLM inference, including all the other information that may land there outside of the prompts. Read that closing clause again, because that is where the whole shift lies. All the other information that may land there outside of the prompts. Prompt engineering is about the text you wrote. Context engineering is about everything else that ends up in front of the model, whether you wrote it or not. The same post draws the contrast directly. Prompt engineering, in their words, is about how to write effective prompts, particularly system prompts. Context engineering is the broader discipline of managing, quote, the entire context state, system instructions, tools, model context protocol, external data, message history, etc. That phrase, model context protocol, is one you will meet properly later. For now, one sentence. The Model Context Protocol, abbreviated MCP, is an open standard for connecting an AI application to external tools and data sources, so that any tool can plug into any agent without a bespoke integration for each pair. That is all you need for the moment. A whole chapter comes later. Now, why is this a different discipline rather than a bigger version of the same one? Because of what the context actually contains once an agent has been running for a while. Think about turn 1. You write a sentence. The context is your sentence, a system prompt, and some tool definitions. Prompt engineering describes that situation well because you wrote nearly all of it. Now think about turn 40. The context is the output of 11 shell commands, 6 files the agent decided to read, 4 of which turned out to be irrelevant, a stack trace, a test run, 3 failed edits, the agent's own reasoning about all of it, and somewhere near the top, your original sentence. You wrote almost none of that. But it is all in front of the model, it is all competing for attention, and it is all shaping what happens next. That is the shift, from composing one instruction well to governing and evolving information state across a loop. It is closer to managing a working set than to writing a good ticket. And the reason it matters is the constraint from the previous chapter. The window is finite, attention spreads thin as it fills, and the model's ability to accurately recall what is in there degrades as the token count rises. Curation is not tidiness. Curation is performance. The Anthropic post names 4 techniques. I want to teach them as principles rather than as features, because the features you will meet in real tools are just implementations of these 4. And once you hold the principle, the features stop looking arbitrary. The first is compaction. Their definition, verbatim, taking a conversation nearing the context window limit, summarizing its contents, and reinitiating a new context window with the summary. You are trading fidelity for room. You will see this in a real tool as an automatic behavior that fires as you approach the limit, and usually as a manual command, you can invoke early with steering instructions about what to preserve. The judgment it asks of you is, what must survive the summary? If the answer is the exact contents of a config file, write that file's path down rather than trusting the summary to carry its contents. The second is structured note-taking. In their framing, the agent regularly writes notes persisted to memory outside of the context window and pulls them back in when needed. This is cheap persistent memory, and I mean cheap literally. A file on disk costs nothing to hold and costs tokens only when read. You will meet this as memory files, as Scratchpad or To-Do files the agent maintains during long tasks, and as project instruction files that are reread each session. The principle underneath is one every engineer already knows. State that must outlive a process should not live in that process's memory. The context window is the process memory. The file system is the durable store. I will add one honest caveat that is my own reasoning rather than a documented finding. Externalized notes have a failure mode of their own, which is staleness. A note written on turn 10 and read on turn 90 is a claim about the world that may no longer be true, and the agent has no automatic way to know that. If you are going to lean on notes, treat them the way you treat a cache. Know what invalidates them. The third is subagent architectures. Verbatim, specialized subagents can handle focused tasks with clean context windows, and they return condensed summaries to the main agent, typically on the order of 1,000 to 2,000 tokens. This is separation of concerns applied to context rather than to code. The example that makes it click is investigation. Suppose you need to know how authentication flows through an unfamiliar service. Answering that honestly means reading maybe 20 files, most of which turn out not to matter. If the main agent does that reading, all 20 files are now sitting in your working context forever, degrading everything that follows. If a subagent does it, the subagent burns its own window on the 20 files and hands back 4 sentences and 3 file paths. Your main context stays clean. The Claude Code documentation puts the reasoning bluntly. Since context is your fundamental constraint, subagents are one of the most powerful tools available. The fourth is just-in-time retrieval. Instead of preloading data into the context, you hold lightweight identifiers, file paths, queries, links, identifiers, and you load the actual content at runtime through tools, only when it is needed. This one deserves a specific warning for anyone arriving from the AI content of 2023, because there is a trap here. You may have absorbed the idea that to make an AI useful over a body of information, you must first build a retrieval-augmented generation pipeline, RAG, which means chunking your content, computing embeddings, storing them in a vector database, and retrieving the top matches by similarity before you generate anything. That is a real technique with real uses. It is largely the wrong technique for source code. Your codebase already has an index. It is called the file system, and the query interface is grep and find and read. An agent given those tools retrieves what it decides it needs, at the moment it needs it, from the live tree, with no embedding pipeline to build, no staleness to manage, and no similarity heuristic silently choosing wrong chunks. In classical RAG, retrieval happens once before generation and is decided by a similarity function. In agentic retrieval, it happens continuously, inside the loop, and is decided by the model. Those are genuinely different systems. RAG remains a good answer for large non-code corpora, documentation, tickets, wikis, and the two compose perfectly well. But you do not need a vector database to point an agent at your repository, and believing you do will cost you weeks. Now the point of the whole chapter. Those 4 principles, compaction, external memory, subagents, and just-in-time retrieval, are why the features in real tools exist and why they are shaped the way they are. Auto-compaction is principle 1. Memory and instruction files are principle 2. The subagent system is principle 3. The file reading and search tools, and the fact that tool definitions themselves are increasingly loaded on demand rather than always, are principle 4. If you learn the tool feature by feature, you get a list to memorize and no way to judge a tool you have not used. If you learn the 4 principles, then when you open any harness, and by harness I mean the software wrapped around the model that runs the loop, holds the tools and assembles the context, you can ask 4 questions of it. How does it compact? Where does it persist state? Can it delegate to a clean context? Does it load information on demand or upfront? Those 4 questions will tell you more about a tool in 10 minutes than a week of tutorials. We now have the resource and the discipline for managing it. The next question is structural. What kind of system are you building around the model in the first place? Because the answer is very often not an agent at all, and knowing when it should not be is a real engineering skill. Chapter 6, Workflows versus Agents. Almost everything being sold as an agent right now is not one. That is not a criticism. In most cases, it is the correct engineering decision, arrived at by accident. But you should be able to tell the difference deliberately, because the two things have different costs, different failure modes, and different debugging stories. The cleanest definition available comes from Anthropic's engineering post, Building Effective Agents, written by Eric Schluntz and Bari Zhang, and published on the 19th of December 2024. Both halves are worth quoting exactly. Workflows, verbatim, are systems where LLMs and tools are orchestrated through predefined code paths. Agents, verbatim, are systems where LLMs dynamically direct their own processes and tool usage, maintaining control over how they accomplish tasks. The distinction is about who holds the control flow. In a workflow, you wrote the control flow. It is in your source, you can read it, and it will do the same thing tomorrow. The model fills in steps. In an agent, the model holds the control flow. It decides what to do next, which tool to reach for, and when to stop. You wrote the tools and the boundaries, not the path. Both are built on the same base unit, which the post calls the augmented model, a language model with retrieval, tools, and memory attached, where the model itself generates its search queries, selects its tools, and decides what to keep. Everything above that line is a question of how much of the sequencing you hand over. Why does this matter for engineering decisions? Because control flow is the thing you can test. A workflow has an innumerable set of paths, so you can write cases for them, reason about worst-case latency, put a number on the cost per run, and reproduce a bug. An agent has an unbounded set of paths. You cannot enumerate them. The cost per run is a distribution rather than a number, and the same input can take a different route on Tuesday. Everything you like about deterministic systems, you are trading away. Sometimes that trade is obviously worth it. Often it is not, and nobody asked. The post names 5 workflow patterns. I want to give each one a shape you would recognize from work you have already done, because 4 of the 5 are things you have built before under other names. Prompt chaining. Decompose the task into sequential steps, with programmatic checkpoints between them. Concretely, Step 1, the model reads a schema and drafts a database migration. Then your code, not the model, runs a linter over the generated SQL and refuses to continue if it fails. Step 2, given the validated migration, the model writes the corresponding data access code. This is a pipeline with gates. You already know why gates help. Each stage gets an easier, narrower task, and a bad output is caught at the boundary instead of propagating. The cost is latency, since the stages are serial. Routing. Classify the input first, then dispatch it to a specialized handler. Concretely, an incoming issue is classified as a typo fix, a dependency bump, or an architectural change. The first 2 go to a cheap, fast model with a narrow prompt and tight tool access. The third goes to an expensive model with a planning step and a human in the loop. This is exactly the reason you put a load balancer, or a message router, in front of heterogeneous work. It also happens to be the single easiest way to control cost, because most of your volume is usually easy. Parallelization. Run models simultaneously in one of 2 shapes. Sectioning means splitting work into independent chunks, for example, applying the same mechanical refactor across 40 files at once, since file 11 does not depend on file 12. Voting means running the same task several times and aggregating, for example, asking 3 independent passes to review a diff for injection vulnerabilities and treating anything 2 of them flag as worth a human look. Sectioning buys you wall clock time. Voting buys you confidence on a task where a single pass is unreliable. Both cost tokens linearly. Orchestrator workers. A central model dynamically breaks the task into subtasks and delegates them. The distinction from parallelization is important, and people miss it. In parallelization, you knew the subtasks in advance and wrote the split yourself. In orchestrator workers, the subtasks are defined at runtime by the model, because you could not know them until you looked. Update every call site of this function is orchestrator workers, because how many call sites there are, and what each one needs, is discovered rather than declared. Evaluator optimizer. One model generates, a second critiques against criteria, and the loop repeats until the critique is satisfied. This is a compiler error loop or a code review loop, with the reviewer automated. It works well when you can articulate the evaluation criteria clearly and when critique genuinely improves the next attempt. If you cannot say what better means, this pattern just burns tokens producing variations. Notice that all 5 have something in common. You can draw them. The boxes and arrows exist in your source code. That is what makes them workflows. So when do you reach for a true agent? The post's answer is precise, and I would treat it as the test. Agents are for open-ended problems, quote, where it's difficult or impossible to predict the required number of steps. That is the criterion. Not difficulty, not importance. Predictability of the step count. If you can say in advance, this is 4 stages, build 4 stages. If the honest answer is somewhere between 2 and 50, depending on what we find in there, you have an agent-shaped problem. Debugging a failing test you have never seen before is agent-shaped, because you do not know how many hypotheses you will have to eliminate. Generating a changelog from commits is not, no matter how much anyone wants it to be. Now the part of this material I find most credible, and I want to flag why before I quote it. The following restraint doctrine comes from Anthropic. Anthropic sells model access, and revenue scales with tokens consumed, and agents consume dramatically more tokens than workflows. This is a vendor with every commercial incentive to tell you to build the most elaborate system you can imagine. Here is what they actually published instead. Verbatim, success in the LLM space isn't about building the most sophisticated system. It's about building the right system for your needs. Verbatim, you should consider adding complexity only when it demonstrably improves outcomes. And on frameworks, verbatim, don't hesitate to reduce abstraction layers and build with basic components as you move to production. That last one is worth dwelling on because it inverts the usual direction of travel. The normal instinct is to prototype with raw pieces and adopt a framework as you harden. The advice here is the opposite. Frameworks are fine for getting started, and as you move toward production, you should be stripping layers out so that you can see what is actually being sent to the model and why. My own view, offered as opinion, is that this is right for the same reason it is right in any distributed system. When something misbehaves at 3 in the morning, every layer of clever abstraction between you and the actual request is a layer you have to peel back before you can see anything. Agent frameworks hide prompt construction and control flow, which are precisely the 2 things that break. So let me make, when not to use an agent, an explicit skill, because nobody teaches it and it is worth real money. Do not use an agent when the step count is knowable. Write the steps. Do not use an agent when you need reproducibility or auditability. If someone will one day ask why the system did a specific thing on a specific date, a predefined code path can answer that, and a dynamic one cannot, at least not without extensive logging you probably have not built. Do not use an agent when latency or cost per run is a hard constraint. An agent's cost is a distribution with a long tail, and the tail is where your budget goes. Do not use an agent when the blast radius of a wrong action is large and you have no mechanical way to constrain it. Dynamic tool selection means you are not choosing the actions anymore, only the action space. And do not use an agent when a deterministic solution already exists. A regular expression, a code mod, or an abstract syntax tree transform will beat a language model on a mechanical transformation every single time, on cost, on speed, and on correctness. Conversely, when the path genuinely cannot be enumerated, a workflow will not save you. You will end up encoding an ever-growing tree of special cases in code, which is the classic sign you have written a worse version of the dynamic system you were avoiding. One honest note on currency. That post is from December 2024, which in this field is a long time ago, and the capability picture has moved substantially since. But the definitions have held up, and I have not found a better or more neutral pair. Judge the taxonomy on whether it helps you decide, not on its publication date. There is one more line from that post, and it is the hinge into the next chapter. The critical property of an agent, verbatim, is that it's crucial for the agents to gain ground truth from the environment at each step, such as tool call results or code execution, to assess its progress. Ground truth from the environment at each step. That is the loop. Let us look at it directly. Chapter 7, the agent loop. The loop is 4 lines. I am going to state it plainly, and then spend the rest of the chapter on why 4 lines are enough to separate a chatbot from an agent, and where those 4 lines will hurt you. The model proposes an action. Something outside the model executes it. The result comes back into the context. Repeat until a stopping condition. That is the whole mechanism. Everything else in this field, the tool schemas, the permission modes, the memory files, the subagents, is scaffolding around those 4 lines. 2 details in there matter more than they look. The first is something outside the model executes it. The model does not run anything. It emits a structured request saying which tool it wants and with what arguments, and your runtime decides whether to honor it. That separation is where every safety control in this course eventually attaches, and it is the subject of the next chapter. The second is the result comes back into the context. This is the part that changes the character of the system entirely. The agent is not predicting what a test run would probably output. It ran the test, and it is now looking at the actual output, exit code, and all. Anthropic's engineering writing calls this gaining ground truth from the environment at each step, quote, such as tool call results or code execution, in order to assess progress. Without that step, you have a very well-read intern who has never once compiled anything. With it, you have something that can be wrong and then find out. Simon Willison, co-creator of Django and one of the most reliable independent chroniclers of this field, makes exactly this the defining line. In his guide on agentic engineering patterns, published in February 2026, he defines the practice as building software using coding agents, tools where, in his words, the defining feature is that they can both generate and execute code, allowing them to test that code and iterate on it independently of turn-by-turn guidance from their human supervisor. Read the end of that sentence twice. Independently of turn-by-turn guidance. Under this definition, a chat assistant that produces a beautiful, correct function is not an agent. It generated. It did not execute, it did not observe, and it did not iterate. You were the loop. You copied the code, you ran it, you read the error, you pasted the error back. The system was you doing the interesting part with a very fast typist attached. Moving that loop inside the machine is the entire step change. You will hear this loop called a RAACT loop, and the term is worth knowing because it is everywhere. RAACT is a contraction of reason and act. It comes from a paper titled RAACT, Synergizing Reasoning and Acting in Language Models, by Shunyu Yao, Jeffrey Zhao, Diane Yu, Nandu, Ishak Shafran, Karthik Narasimhan, and Yuan Cao, posted to archive on the 6th of October 2022, and later published at the 2023 ICLR conference. The abstract describes generating, quote, both reasoning traces and task-specific actions in an interleaved manner, allowing for greater synergy between the two. Reason, act, observe, repeat. Now the honest caveat, because this one gets overstated constantly. Modern coding tools do not literally implement the prompting format from that paper. Native tool calling interfaces and built-in extended reasoning absorbed the idea and made the original scaffolding unnecessary. When someone today says a RAACT loop, they almost always mean the general reason-act-observe shape, not the paper's technique. Know the paper as the ancestor. Do not claim your tool runs it. So if the loop is old news from 2022, why did coding agents only start working recently? The most credible answer I have found comes from Andrej Karpathy, writing publicly in February 2026, describing a change he dates to December 2025. Verbatim in part, the models have significantly higher quality, long-term coherence and tenacity, and they can power through large and long tasks. Tenacity is the word to hold on to. The loop always worked in principle. What changed is that a model became able to run it 40 times without losing the plot, without forgetting the original goal and without giving up 2 steps before the answer. A loop whose body degrades after 5 iterations is not a useful loop. That is a capability property, not an architecture property. And it is why the architecture from 2022 only became productive very recently. Now, how do you actually drive this thing? The doctrine in the Claude Code documentation is a 4-phase shape: explore, plan, implement, commit. Explore means letting the agent read and reason without editing anything. Most tools expose this as a plan mode. The documentation describes it precisely. Plan mode tells the model to research and propose changes without making them. It reads files, runs shell commands to explore, and writes a plan, but does not edit your source. Plan means turning that exploration into a written plan you actually read. Implement means executing against that plan. Commit means landing the work in version control while the reasoning is still fresh. If that sounds like ordinary professional practice, it is. That is rather the point. The reason to be explicit about it is that the plan is a written artifact you can review before any code exists, which is the cheapest possible moment to catch a wrong approach. And here is the caveat that makes this doctrine credible rather than preachy, stated in the documentation itself. Planning has overhead. Quote, "If you could describe the diff in 1 sentence, skip the plan." Planning pays off when the approach is genuinely uncertain, when the change spans multiple files, or when the code is unfamiliar to you. It does not pay off when you want a null check added to a function you wrote last week. A course that told you to always plan would be selling you ceremony. Use the phase structure where the uncertainty is, and skip it where there is none. One more thing about plan mode, since it is easy to overtrust. In configurations where permissions can be bypassed, plan mode's restriction is not mechanically enforced. The model is instructed to plan without editing. Plan mode is a permission setting, not a sandbox. That distinction, instructed versus enforced, is going to keep coming back, and every time it does, it is the same lesson. Now the stopping condition, which is where I want to leave you uncomfortable, because this is the most dangerous single property of the agent loop. A loop needs a termination condition. In practice, there are 4. The goal is verifiably achieved, the budget runs out, a human interrupts, or the model concludes that it is done. Notice how different the last one is from the other 3. 3 of them are external and mechanical. The 4th is the model's own judgment about its own work. The Claude Code documentation states the problem in 1 sentence, and I think it is the most important sentence in the entire practice literature. Quote, "Claude stops when the work looks done. Without a check it can run, looks done is the only signal available, and you become the verification loop." Sit with the shape of that failure. The agent is not lying to you. It genuinely assessed the work and concluded it was finished. It is not concluding this from evidence, because it has no evidence, because nobody gave it away to get any. So it is doing pattern matching on what finished work usually looks like. And here is the cruel part. The more capable the model, the more convincing its output looks when it is wrong, and the less likely you are to check. That last inference is mine, not a documented finding, but it matches the failure I see most often. The fix is structural rather than motivational. You do not solve this by asking the agent to be more careful. You solve it by giving the loop something real to terminate against: a test suite, a build-exit code, a linter, a diff against a fixture, a screenshot comparison, anything that produces a fact rather than an opinion. The documentation's framing is to ask for evidence, the test output, the command result, not assertions. And there is an escalation ladder from an instruction in the prompt to a session-level goal condition rechecked each turn, to a hook that deterministically blocks the turn from ending, to a separate verification agent with a fresh context that rechecks the work. The higher you go, the less it depends on the model choosing to comply. 2 related loop pathologies to recognize while we are here. Infinite exploration, where the agent reads and never converges, usually because the goal has no verifiable end state. And the correcting over and over trap, where you fix the same mistake repeatedly in 1 session. The documented guidance on that second one is sharp. If you have corrected it more than twice on the same issue, the context is now cluttered with failed approaches, and you should clear the session and restart with a better prompt rather than keep pushing. You are not persuading a colleague. You are poisoning a working set. Give the loop a real stopping condition, and it becomes an engineering tool. Leave looks done as the only signal, and you have automated the typing and kept all the checking. We will come back to verification properly, because it is the highest leverage habit in this entire field. But first, the mechanism underneath every single one of these steps. When the model asks for an action, what does that actually look like on the wire, and who runs it? That is tool use, and it is next. Chapter 8, Tool Use and Function Calling. Here is the fact that surprises nearly every engineer the first time they look under the hood. The model cannot do anything. It cannot read a file. It cannot run your test suite. It cannot open a socket. It has no hands. What it can do is ask. When you watch an agent run your tests, what actually happened is that the model emitted a structured request, a tool name and a set of arguments, typically as JSON conforming to a schema you defined. Your code received that request, decided whether to honor it, ran the command, captured the output, and fed the output back into the next model call. The model never touched your machine. Your code did on the model's suggestion. Hold on to that, because a great deal of this course falls out of it. The model only ever asks. Everything it appears to do is something your code chose to do on its behalf. Let me walk the round trip concretely. Using the shape Anthropic documents for its messages, a PI the field names differ between vendors. The mechanics do not. Step 1. Your request to the model carries, alongside the conversation, an array of tool definitions. Each tool is 3 things: a name, a description, and an input schema written in JSON schema. That is all. There is no code in a tool definition. You are handing the model a menu, not a library. Step 2. The model replies. If it wants a tool, the reply comes back with a stop reason of tool use, plus 1 or more tool use blocks, each carrying an identifier, the tool name, and the arguments it has filled in. In Anthropic's own words, from the tool use overview documentation, Claude determines when to call a tool based on the user's request and the tool's description. It then returns a structured call that your application executes. Step 3. Your code executes it. This is the step with all the engineering in it. You validate the arguments. You apply your permission rules. You decide whether this particular shell command is allowed to run at all or whether to stop and ask the human. Every approval prompt you have ever seen in a coding agent lives right here, in Step 3, in ordinary code that you or your vendor wrote. Step 4. You send a follow-up request containing a tool result block that references the original tool use identifier and carries whatever came back. The model then produces its answer or asks for another tool. Repeat steps 2 through 4 and you have the agent loop. That is the whole trick. An agent is a while loop around a chat completion with a tool dispatcher in the middle. There is less magic here than the marketing implies, and that is good news because it means the behavior is yours to engineer. A word on names. Function calling is what OpenAI called this when it shipped in 2023. Tool use is Anthropic's name for it. They are the same concept with different JSON field names, and both are now near universal across providers. Neither term is wrong, and you will hear both in the same meeting. One distinction worth carrying. Client tools run in your application, your file editor, your shell, your database query. Server tools, such as web search or code execution, run on the provider's infrastructure, and the results come back to you without your handling execution at all. Identical from the model's point of view. Very different from yours, because with a server tool, somebody else's machine decides what runs. There are also controls on the request itself. You can force the choice. Let the model decide, require that it use some tool, require one specific tool, or forbid tools entirely for a turn. You can turn off parallel calls. You can ask for strict schema conformance so the arguments are guaranteed to match the shape you declared rather than merely usually matching it. These are unglamorous knobs, and they are how you turn a probabilistic system into something a downstream parser can live with. Now the part practitioners underrate. The name, the description, and the schema of every tool are read by the model. They are not documentation for your colleagues. They are prompt surface. Sit with what that means. If your tool is called Do It, described as does the thing, the model has no basis on which to choose it correctly, and it will misfire. If two tools have overlapping descriptions, you have built an ambiguity directly into the model's decision procedure, and you will watch it pick the wrong one under load. If a schema field is called id with no description, you will get the wrong identifier in it, and no amount of prompting elsewhere will fix a bad signature. This is the same class of work as designing a clean interface for a new hire who has read your signatures and never your source. Except this new hire reads only the signatures, every time, forever, and never asks a clarifying question in the corridor. That framing has a darker edge, which Chapter 10 develops properly. Because the description is text going into the model's context, a tool description written by somebody else is an instruction written by somebody else. Security researchers at Invariant Labs demonstrated exactly that attack against tool servers in April 2025. Park it for now, it comes back. Then there is the cost, which catches almost everyone. Tool definitions are input tokens on every single request. A token is the unit of text the model is billed and bounded in, roughly a word fragment. And in an agent loop, the entire conversation is resent on each turn, so your tool definitions are not a one-off startup cost. They are paid again on turn 1, turn 2, and turn 40. There is also a hidden preamble the provider injects to teach the model the tool calling format, and that is billed too. Anthropic publishes those counts per model. For one current model, with automatic tool choice, the published figure is 286 tokens. Trivial in isolation. Now add 20 tool definitions you never use. This is why loading hundreds of tools is genuinely expensive rather than merely untidy. Every unused tool is a recurring tax on every turn, and the damage is worse than the token bill suggests, because a longer context measurably degrades the model's ability to use anything in it. The vendors have responded mechanically. Claude Code now defers the tool definitions of external tool servers by default rather than loading them all up front, and offers a tool search tool for large catalogs. That design choice is the tell. If loading everything were cheap, nobody would have built the deferral. My rule, and I will label it as opinion rather than a documented finding. A small, well-named, non-overlapping tool set beats a large one nearly every time. If you cannot explain to a colleague in one sentence when each tool should be chosen over its neighbors, the model cannot make that choice either. What would change my mind is evidence that models select reliably from very large catalogs. The fact that vendors are building search over tools rather than just loading them suggests they do not yet. 2 mechanics to finish. First, parallel tool calls. Notice that step 2 said 1 or more tool use blocks. A model can request several independent tools in a single reply, and a decent harness executes them concurrently and returns all the results together. That is a straightforward latency win when the calls are genuinely independent. Read 4 files at once instead of 4 sequential round trips. Providers expose a switch to disable it, which you want when your tools have side effects that must be ordered. Second, errors. Your instinct as an engineer will be to catch the failure and hand back something tidy. Resist it. The error text is the most useful thing you can give the model. Anthropic's guidance on agent design makes the point that agents need to gain, in their phrase, ground truth from the environment at each step in order to assess progress. A stack trace, a compiler error, a failing assertion, that is ground truth. A polite operation unsuccessful is not, and an agent given only that will guess. There is a failure mode here worth naming, though I want to be straight about its evidential status. It comes from user-filed issue reports rather than a controlled study, so hold it loosely. The report is that once a single malformed tool call lands in the conversation history, later calls start imitating it. The mechanism is at least plausible. History is resent every turn, so the malformed call sits in context as an example of what a tool call looks like here. If that is right, the failure is absorbing rather than transient, and retraying will not clear it. You have to remove the bad turn from the history. If you ever watch an agent break and then stay broken in the same specific way, that is the first hypothesis I would test. So, tool use is a conversation protocol, not an execution mechanism. The model proposes, your code disposes, and the quality of everything that happens in between is entirely yours. Which raises the obvious question. If the model only ever asks, then the thing that decides what actually happens is the real product. That layer has a name, and it is the subject of the next chapter. Chapter 9, Harness Engineering. Ask an engineer which coding agent is best and you will get an answer about models. Which model writes better code, which one scores higher, which one is worth the money. It is the natural question, and I think it is usually the wrong one. Here is the term that explains why. A harness is everything wrapped around the raw model that turns it into a working agent. Concretely, that means the loop that calls the model and dispatches its requests. The implementations of the tools themselves, the permission and approval logic that decides which of those requests actually run. The context assembly, which chooses what to put in front of the model on each turn, and the compaction that summarizes the conversation when it runs out of room. The memory files that get loaded at startup, the system prompt, the sandbox, the subagents, and the checks that catch it when it is wrong, the tests, the linters, the type checker, the review. The model is the engine. The harness is the rest of the car. You do not get to change the engine, and if you could, it would not help as much as you expect. What you build is the rest of the car. Birgitta Berkeler of ThoughtWorks put this more compactly than I can, writing on martinfowler.com on the 2nd of April 2026. Her formulation, verbatim, agent equals model plus harness. 3 words, and it reorganizes the whole field. Her decomposition of the outer harness is the most useful map I have found, so let me give it to you. She splits it into guides and sensors. Guides are feed-forward controls, things that anticipate and prevent unwanted behavior before it happens. Your instructions, your skills, your plans, your architectural constraints. Sensors are feedback controls, things that observe the result and enable self-correction. Each of those have splits again into computational elements, which are deterministic, like tests and linters and type checkers, and inferential elements, which are themselves AI-based, like a review agent. Human steering sits on top of the whole system. 2 of her sentences are worth quoting exactly, because they set the design goal. First, a well-built outer harness serves 2 goals. It increases the probability that the agent gets it right in the first place, and it provides a feedback loop that self-corrects as many issues as possible before they even reach human eyes. And second, which is the one I would put on the wall? A good harness should not necessarily aim to fully eliminate human input, but to direct it to where our input is most important. That is a control system's view of the problem, and it should feel familiar. You already know how to build systems that are unreliable in the small and dependable in the aggregate. You do it with retries, with idempotency, with health checks and circuit breakers and CI gates. This is the same discipline pointed at a new source of unreliability. Practitioners distinguish an inner harness from an outer one. The inner harness is what the vendor ships, the agent's own loop, its built-in tools, its system prompt, the parts you cannot see or modify. The outer harness is what you build on top, your memory files, your skills, your hooks, your CI gates, your permission configuration. Almost everything you will actually do is outer harness work. I should flag that this inner-outer split is a widely used framing rather than a formal standard, and different authors draw the line in different places. Use it as a thinking tool, not as a specification. Now the claim I want you to take away from this chapter. The same model in 2 different harnesses behaves so differently that comparing models without holding the harness fixed tells you very little. The strongest public evidence for that is sitting in plain sight on the benchmark leaderboards. Terminal Bench, the benchmark for agents operating in a real shell, does not report model scores. It reports agent and model pairs. The harness is named as part of the system under test because the people who built the benchmark understood that it is part of the system under test. That is a quiet but serious concession, and it is the single most pedagogically useful thing about that leaderboard. Meanwhile, the numbers that appear in model launch announcements usually do not tell you what scaffold produced them. There is sharper evidence from the failure side. When engineers point a coding harness at a different model to save money, the swapped model frequently looks, in their words, dumber. Several documented cases show the harness was at fault rather than the model. In one, the harness could not detect the real context limit of a third-party endpoint and fell back to a hard-coded default of 200,000 tokens. Pointed at a provider genuinely serving 1 million tokens of context, it therefore began summarizing and discarding conversation at roughly 19% of the real capacity. The user-visible symptom is exactly the complaint you would expect. It keeps forgetting what it was doing. The user blames the model. The model was fine. In another case, a translation layer sitting between the harness and the model corrupted the arguments of tool calls. The reported measurement was 10 out of 10 valid tool calls with that translation component switched off, and 0 out of 10 with it switched on, with the model held constant. I want to be honest about what these are. They are user-filed issue reports, not controlled studies, so treat the specific numbers as illustrative rather than authoritative. But the direction of the lesson is well supported by everything else in this chapter. When an agent behaves badly, the harness is at least as likely a suspect as the model, and it is the suspect you can actually interrogate. So here is my opinion, labeled as opinion. For most teams, most of the time, harness quality dominates model choice within the current frontier tier. The honest answer to why did it work brilliantly for them and terribly for me is almost never that they had a better model. It is that they had better context, better tools, better verification, and better constraints. What would change my mind is a rigorous comparison that holds the harness completely fixed across models and shows the model gap dominating. I have not seen one. If you find one, it should update you and me both. I also want to be careful not to oversell the term itself. Harness engineering is fast-emerging vocabulary from 2025 and 2026. It is not a standard with a specification behind it. What I can tell you is that it is not one vendor's marketing coinage. ThoughtWorks names harness engineering as a discipline in its own right, covering context engineering, architectural constraints, and code-based maintenance, and ThoughtWorks does not sell you a model. Adi Osmani writes about agent harness engineering independently of them. That is enough corroboration to treat it as a real term with real content. It is not enough to treat any particular decomposition of it as canonical, and you will meet people using the word in narrower senses, sometimes meaning only the code that runs the loop, sometimes only the scaffolding around evaluation. When you hear it, ask which sense they mean. Let me leave you with the highest leverage piece of harness work I know, because a chapter like this should end with something you can do on Monday. Give the agent a way to verify its own work. Anthropic's own best practices documentation states the problem exactly. Claude stops when the work looks done. Without a check it can run, looks done is the only signal available, and you become the verification loop. That is the trap. If there is no test, no build, no linter, no diff against a fixture, no screenshot comparison, then the agent's only stopping criterion is its own judgment that things appear finished, and you become the censor, manually, forever. The enforcement of that check comes in escalating levels, and knowing the latter is worth more than any prompt trick. At the bottom, you ask for it in the prompt. Above that, you make it a session-level goal condition that gets rechecked each turn. Above that, you use a hook, which blocks the turn from ending until the check passes and does so deterministically. At the top, you have a separate verification agent with a fresh context recheck the work. And the crucial detail throughout, ask for evidence, not assertions. Test output, command exit codes, real artifacts, not the sentence all tests pass. That latter captures a distinction that will keep recurring. Instructions are advisory. The documentation is blunt about it. Unlike written instructions, which the model reads and tries to follow, hooks are deterministic and guarantee the action happens. If you need a guarantee, an instruction is not one. So the harness is the product, and building it is the job. The next question is how the tools inside it get there in the first place, because writing every integration by hand does not scale. There is a standard for that now, and it is the subject of the next chapter. Chapter 10, the Model Context Protocol. The Model Context Protocol. From here on I will call it MCP, as everyone else does. Start with the problem it solves, because you have solved that problem before in other clothes. An agent is only as useful as the systems it can reach. You want it to query your database, read your issue tracker, hit your internal service. Before MCP, every one of those connections was a bespoke adapter. If you had N agent applications and M tools, you were on the hook for N times M integrations, each written by somebody with their own idea of how tools should be described, each breaking independently. That is the shape that produced ODBC and Language Server Protocol and every other standard that exists because the alternative was quadratic. MCP is the standard for that. The specification's own analogy, verbatim, is think of MCP like a USB-C port for I applications. Just as USB-C provides a standardized way to connect electronic devices, MCP provides a standardized way to connect I applications to external systems. That analogy is doing real work. A protocol does not make your tools better, it makes them interchangeable. Technically, it is an open standard built on JSONRPC, version 2.0, with a data layer defining the message schema and a transport layer defining how connections are established and authorized. Now the architecture, in plain terms, because this is where people get muddled. There are 3 participants, and the specification defines them like this, verbatim. An MCP host is the AI application that coordinates and manages one or multiple MCP clients. An MCP client is a component that maintains a connection to an MCP server and obtains context from an MCP server for the MCP host to use. And an MCP server is a program that provides context to MCP clients. Translate that. Your coding agent or editor, whatever you are sitting in front of, is the host. For each server you configure, the host spins up one client, and that client holds one connection. The client is not a separate application you install. It is a piece of the host. Configure 5 servers and your host has 5 clients. The most common confusion is the word server. It says nothing about where the thing runs, and a great many MCP servers are local processes on your own laptop. Which brings us to transports, and to something a lot of tutorials get wrong. There are 2 transports in the current specification. The first is standard input and output, usually written as SDDO. The host launches the server as a child process, and they talk over the process's own input and output streams. No network, no ports, no latency. That is how most local servers work. The second is streamable HTTP, for remote servers. The client posts messages over HTTP, with servers and events available as an optional streaming mechanism inside that transport, and with bearer tokens or a PI keys or OAuth for authorization. The thing to unlearn? Older material lists 3 transports, naming SDDO, HTTP, and SSE as siblings. The standalone HTTP+ server-sent events transport from the original 2024 specification is no longer a separate transport. If a tutorial lists 3, it is out of date, and that is a useful canary for how old the rest of it is. Next, the 3 things a server can expose. These are called primitives, and the specification describes them like this, verbatim. Tools are executable functions that AI applications can invoke to perform actions, such as file operations, API calls, database queries. Resources are data sources that provide contextual information to AI applications, such as file contents, database records, API responses. And prompts are reusable templates that help structure interactions with language models, such as system prompts and few-shot examples. There is a sticky teaching heuristic here. Tools are model-controlled verbs, resources are application-controlled nouns, prompts are user-controlled templates. That phrasing is a widely circulated teaching device, not specification language, but the distinction underneath it is real. The model decides to call a tool. The application decides which resources to pull in. The user picks a prompt. On governance, because provenance affects how much you should trust a standard. MCP was created by Anthropic in 2024 and then donated to the Agentic AI Foundation, a directed fund under the Linux Foundation, announced on the 9th of December 2025. That foundation was co-founded by Anthropic, Block, and OpenAI, with Google, Microsoft, AWS, and Cloudflare among its platinum members. So this is no longer one company's protocol. As for scale, the project's own December 2025 announcement cited more than 97 million monthly SDK downloads and 10,000 active servers. Those are self-reported figures rather than an independent audit, so treat them as an order of magnitude rather than a measurement. The specification is also moving quickly. In the current version, MCP has become stateless, with per-request capability negotiation replacing the old session handshake, and 2 client-side features have been deprecated. There is also a working group on carrying skills over MCP, which is the next chapter's subject, and a sign that these mechanisms are converging rather than competing. Practical advice. Check the specification version before trusting anything you read about MCP, including this chapter. So when is MCP the right answer? And when is it an expensive way to do something simple? It earns its keep when you need live access to an external system, a database behind credentials, a ticketing system, an internal service with its own auth, anything remote and stateful. It gives you a uniform description of the capability, a consistent authorization story, and it works across every host that speaks the protocol. It is the wrong choice when the thing already has a decent command line interface and your agent already has a shell. That is the mistake I see most often. If you want the agent to read files, search code, run Git, or hit an API that ships a CLI, it can simply do that. No server, no protocol, no network, and no permanent token cost. Because every tool an MCP server exposes is a definition sitting in the model's context on every turn, whether you use it or not. That rule of thumb is mine rather than a vendor recommendation, but it follows directly from how tool definitions are built, and clients now defer loading MCP tool definitions by default for exactly this reason. And then the part that gets skipped, which I will not skip. Connecting a third-party MCP server means running someone else's code with your agent's permissions. For a local server, that is literal. A binary you downloaded and executed with your own privileges, distributed like any other package, frequently unpinned. Every supply chain risk you already know applies, plus one that ordinary packages do not have. That extra channel is this. A tool's description is not documentation. It is text injected verbatim into the model's context. Invariant Labs published this in April 2025 under the name tool poisoning. A malicious server writes instructions into the description field, and because your approval interface shows a short name and a truncated description, the payload is invisible to you while fully visible to the model. 2 related attacks are worth naming. A rug pull serves a benign description at approval time and swaps it later, because approval is a one-time event and the description is not. Tool shadowing means one server's description alters how the agent uses another server's tools, which is to say that trust does not compose. The specification is candid about all of this. It states that MCP cannot enforce these security principles at the protocol level, and, verbatim, that tools represent arbitrary code execution and must be treated with appropriate caution, and that descriptions of tool behavior such as annotations should be considered untrusted, unless obtained from a trusted server. The operative principle is that a server is trusted for capability and never for content. How bad is this in practice? A benchmark called MCP Talks built on 45 live real-world MCP servers and 353 genuine tools, reported an average attack success rate of 36.5% across model settings. The finding to remember is the counterintuitive one. More capable models were often more vulnerable because the attack exploits good instruction following. Capability does not buy safety here, it buys compliance. The deeper danger is not any single server. It is combination. Give one agent access to your private data, expose it to content an attacker can influence, and let it communicate outward, and you have assembled a serious vulnerability out of 3 individually reasonable decisions. Simon Willison named that combination the Lethal Trifecta, and it is the mechanism behind most of the real incidents in this field. Chapter 17 takes it apart properly, and Part 3 of this series builds the defenses. For now, 4 cheap controls. Pin your server versions, because pointing at latest in a config file is a standing invitation to a rug pull. Read tool descriptions as code, not as documentation. Scope credentials to the task, because the published exfiltration proofs of concept generally worked only because a token could reach more than it needed to. And keep your agent configuration files under version control and diff them, because injecting a rogue server into them is a documented persistence technique. MCP connects your agent to systems. It does not teach your agent how your team does things. That is a different problem with a different, much cheaper mechanism, and it is next. Chapter 11, Skills and Progressive Disclosure. An agent skill is a folder with a markdown file in it. That is genuinely the whole format. The file is conventionally called skill.md, and it opens with a small block of metadata carrying 2 required fields, a name and a description, followed by ordinary markdown instructions. The folder may also bundle scripts, reference documents, and assets that the instructions point at. The open specification describes it, verbatim, as follows. Agent skills are a lightweight, open format for extending AI agent capabilities with specialized knowledge and workflows. What goes in one? Domain knowledge or a repeatable procedure. How your team cuts a release. How a database migration is written in this particular codebase with its particular rollback convention. The accessibility checklist a new component has to clear. The format your incident write-ups take. Anything you would otherwise explain to a new colleague the 3rd time they hit it, and then find yourself explaining again. If that sounds like documentation, it is, with one difference that changes everything. The agent decides when to read it. That mechanism has a name, and it is the concept to take from this chapter: progressive disclosure. The specification lays it out in 3 stages, and I will quote it because the precision matters. Stage 1, discovery. At startup, agents load only the name and description of each available skill, just enough to know when it might be relevant. Stage 2, activation. When a task matches a skill's description, the agent reads the full skill.md instructions into context. Stage 3, execution. The agent follows the instructions, optionally executing bundled code or loading referenced files as needed. Consider the economics of that. The always-on cost of a skill is its name and description, which is on the order of tens of tokens. A token, again, being the unit of text the model is billed and bounded in. So 100 skills sitting in your repository cost you approximately nothing until one of them becomes relevant. The body is paid only when it is used. This is not a capability technique. It is a context budget technique, and it is the cleanest answer anyone has yet found to the problem of having more to tell the agent than fits in front of it. 2 consequences follow, and they are the practical craft of writing skills. First, the description is the load-bearing field. It is the only part the agent sees when deciding whether this skill is relevant. A description that says, release stuff, will not be found. A description that says, use when cutting a production release, tagging a version, or publishing to the package registry, will be. Write descriptions for retrieval, not for elegance. Second, once a skill loads, it stays in context for the rest of the session. The documentation is explicit that this is a recurring token cost and recommends keeping the main file under 500 lines, pushing detail into separate reference files that the body points at only when needed. Progressive disclosure has a third tier for a reason. Use it. On provenance, since a format is only as useful as its adoption. Skills were developed by Anthropic and released as an open standard with a public specification and repository. At the time of this research, the adopting list spans Cursor, GitHub Copilot and VS Code, OpenAI Codex, Gemini CLI, JetBrains Juni, OpenCode, OpenHands, Goose, AMP, and a long tail beyond that. That is one of the clearest convergences in this field, and it is worth noticing because most things in this space are still vendor-specific. There is also a working group on carrying skills over the model context protocol, so the boundary between these mechanisms may move. One current events note for Claude Code users specifically: custom / commands have been merged into skills. A file defining a command and a skill of the same name now produce the same thing and work the same way, with existing command files still functioning. If you learned this tooling 6 months ago, that is a change. Now to the part that actually matters, and the reason this chapter exists. You have 3 ways to extend an agent, and choosing correctly between them is a real engineering judgment with a real cost attached to getting it wrong. Here is the framework. Memory files load every session. Whether the file is called Claude.md or agents.md, depending on your tooling, the property is the same. It is read at startup every time, and it occupies context whether or not this session has anything to do with its contents. Therefore, memory files are for things that apply broadly. The stated test from the documentation is a good one. Would removing this line cause the agent to make mistakes? If not, cut it. Concretely, the command that runs your tests because the agent cannot guess it. The fact that you use one package manager and not another. A build step with a non-obvious flag. Repository etiquette, like which branch to target. Architectural decisions that are not visible from any single file. Environment quirks. Exclude anything the agent could derive by reading the code, anything that is a standard convention it already knows, detailed a PI documentation, and anything that changes weekly. And there is a hard limit on this that surprises people. It is not merely that a bloated memory file costs tokens. The documentation states plainly that bloated files cause the agent to ignore your actual instructions. The guidance is to target under 200 lines. This is the failure mode where somebody writes an 800-line file full of rules, watches the agent violate Rule 412, and concludes the model is stupid. The model is drowning. There is a useful diagnostic in the same guidance. If a rule keeps being ignored, your file is probably too long, and if the agent asks you something the file already answers, your phrasing is ambiguous. Skills load on demand. Therefore, skills are for knowledge that is relevant only sometimes. The official guidance says this in one sentence, verbatim. For domain knowledge or workflows that are only relevant sometimes, use skills instead. That single sentence is the whole distinction. The release procedure does not need to be in front of the agent while it fixes a typo in a test. The migration convention does not need to be loaded while it reads logs. Move them out of the always-on file and into skills, and you get both effects at once. Less context burned, and a shorter memory file that the agent actually follows. MCP, the Model Context Protocol, is for connecting to external systems and live data. It adds capabilities over a wire protocol with a running server behind it. That is the right tool when the agent needs to reach a database, a ticket tracker, a design tool, an internal service behind authentication. It is the wrong tool for teaching procedure. The rough rule, which I find holds up. MCP gives the agent new capabilities and connections. Skills teach it how to do a job properly with capabilities it already has. And they compose. A perfectly good skill is one that explains how and when to use a particular MCP server's tools and in what order and what to check afterwards. Now the fourth thing, which the three-way framing hides and which you must not miss. None of these three enforce anything. The documentation is unambiguous. The agent treats them as context, not enforced configuration, and to block an action regardless of what the model decides, you need a hook. A memory file saying never push to main is a suggestion with a high prior probability of being followed. It is not a guarantee, and engineers who confuse the two build systems that are safe right up until the day they are not. So here is your decision procedure, and this is the kind of judgment a certification should test, because it is not recall, it is a trade-off with axes. Does it apply to essentially every session in this repository? Memory file and keep it short. Does it apply only sometimes, and is it knowledge or procedure rather than access? Skill. Does it require reaching a system outside this machine with live state or credentials? MCP server and read Chapter 10 again before you install one. And does it have to happen no matter what the model decides? Then none of the three. That is a hook or a permission deny rule. Run those 4 questions against anything you are tempted to add, and you will avoid the most common self-inflicted wound in this whole discipline, which is the 1,000-line instruction file that quietly stops working. That brings us to the always-on layer itself, which deserves a chapter of its own. What belongs in a memory file, how the different scopes stack, and why the file everyone writes first is usually the file causing their problems. Chapter 12. Memory files and prime directives. Imagine onboarding an engineer who is fast, widely read, and genuinely capable, but who arrives every morning with no memory of the day before. You would not re-explain the whole system each time. You would write it down once, put the document somewhere they always look, and keep it short enough that they actually read it. That is precisely the problem a memory file solves. A coding agent starts every session from nothing. It does not know that your test command is not the obvious one. It does not know that the directory called legacy is load-bearing. It does not know that you migrated off the object relational mapper 2 years ago and that half the examples still sitting in the tree are the old way. The mechanism is unglamorous. It is a plain markdown file committed to the repository that the agent reads at the start of every session before it does anything else. In Anthropic's tooling, that file is called Claude.md. In the wider ecosystem, the same idea has a different name, Agents.md, described on its own site as a simple, open format for guiding coding agents, used by over 60,000 open-source projects. Agents.md is now stewarded by the Agentic AI Foundation, a fund under the Linux Foundation, having been contributed by OpenAI as one of its anchor projects in December 2025. Have the two converged? Not at the file name level. The Claude code documentation is blunt about it. Claude code reads Claude.md, not Agents.md. The documented bridge is an import line, one file pulling in the other, or a symbolic link. So you can keep a single source of truth. You just cannot assume one file name works everywhere. That is the state of play as of August 2026, and it is worth knowing before you spend an afternoon arguing about it. There is a scope hierarchy, and it behaves the way you would hope. There is a machine-wide managed policy file for organizations, a user-level file in your home directory that applies to everything you do, a project file checked into the repository for the team, and a local file, gitignerd, for your personal quirks. Files closer to the working directory are read last. The important detail is that all discovered files are concatenated, not overridden. Your personal preferences do not replace the team's rules. They stack on top of them. Now the part that matters more than the plumbing. What goes in the file? 6 kinds of thing earn their place. Commands the agent cannot guess, because your build is not the default build. Style rules that differ from defaults, because the model will otherwise apply the community norm and be reasonable and wrong. The test runner, specifically, including the incantation for a single test file. Repository etiquette, branch naming, commit conventions, whether it may amend, whether it may push. Architectural decisions and the reasoning behind them, because the agent cannot infer intent from structure. And environment quirks and non-obvious gotchas, the tribal knowledge you would tell a new hire in their first week over coffee. 4 kinds of thing do not belong. Anything derivable by reading the code, because the agent can read the code and will do it more accurately than your summary. Standard conventions the model already knows, and it knows more of them than you think. Detailed API documentation, which bloats the file and goes stale. And anything that changes often, because a memory file that is confidently wrong is worse than a memory file that is silent. The discipline that holds all of this together is one question, and it is the most useful sentence in Anthropic's published best practice guidance. For each line, ask, would removing this cause the agent to make mistakes? If the answer is no, cut the line. Not, is this true? Not, is this nice to know? Would its absence cause an error? Run that test on every line, every time you touch the file, and be ruthless, because the published size guidance is to target under 200 lines, and you will blow through that within a month if you are not. Which brings me to the thing engineers find hardest to believe, and the reason the discipline is not optional. A bloated memory file causes the agent to ignore your actual instructions. That is close to a direct quotation from the official guidance, and the documentation states the mechanism plainly elsewhere. Longer files consume more context and reduce adherence. More rules produce less compliance, not diminishing returns, negative returns. Your instinct on hearing that will be to disbelieve it, because in every other system you have worked with, adding a constraint adds a constraint. Here is my read of why it does not hold, and I will label this as my inference rather than a documented finding. It is the same phenomenon as context rot, the well-documented effect where a model's ability to accurately recall information from its context degrades as that context grows. A memory file is context. Every line you add dilutes the attention available to every other line, including the 3 lines that actually mattered. The human analogy is exact, and you have lived it. Nobody reads the 400-page coding standards document, and the team that writes one has less consistent code than the team with a 1-page checklist on the wall. 2 diagnostics fall straight out of this, and both are cheap. First, if you keep finding a rule ignored, the file is probably too long. The instinct is to write the rule again in capital letters with exclamation marks. Resist it. Delete something else instead. Second, if the agent asks you a question the file already answers, the file is not too long. The phrasing is ambiguous. Rewrite that line, do not add another. Now the most important caveat in this chapter, and the one that gets people hurt. Everything in a memory file is advisory. The documentation is explicit. The agent treats them as context, not enforced configuration. And more explicitly still, the file's content is delivered as a user message after the system prompt, not as part of the system prompt itself. The model reads it and tries to follow it, but there is no guarantee of strict compliance. Read that again with your security hat on. If you write "never push to main" in your memory file in capitals with 3 exclamation marks, you have expressed a strong preference. You have not built a control. You have a high prior probability of compliance, not a guarantee. And you already understand this distinction perfectly well from every other part of your stack. A comment saying, "Do not call this directly," is not a private method. A note in the README is not a firewall rule. The deterministic counterpart is a hook. A hook is a script the harness runs at a defined point in the agent's lifecycle, before a tool call, after a tool call, when a turn tries to end. The official wording draws the line cleanly. Unlike memory file instructions, which are advisory, hooks are deterministic and guarantee the action happens. The same is true of a deny rule in your permission settings, so the placement rule is simple. If the consequence of a rule being violated is something you would have to explain to somebody, it belongs in a hook or a deny rule, not in prose. That brings me to the term agent prime directives. You will encounter it, and you should handle it carefully. I went looking for it in the documentation of Anthropic, OpenAI, Google, and the Agentic AI Foundation. It is not there. It is not a standard, and I am not going to pretend otherwise. In practice, the phrase is used in at least 3 unrelated senses. As a colloquial nickname, borrowed from Star Trek, for the top priority standing instruction at the head of a memory file. As the name of one individual's branded methodology, promoted by press release. And in the AI ethics literature as an Asimov-style overriding safety rule, which has nothing to do with coding agents at all. There is also a company with a similar name. There is no authority to borrow here. The idea underneath, though, is real and worth teaching. Agents follow a precedence order. The harness's own system prompt sits above the project memory file, which sits above what you type in the session. The top of that hierarchy is where a small set of standing, non-negotiable rules belongs. 3 to 5 of them, no more. Never commit secrets. Always run the test suite before claiming a task is done. Ask before making an architectural decision. Calling those your prime directives is a perfectly fine naming convention inside your team. Presenting them as an industry standard is not, and eventually somebody will call you on it. One last placement rule, and it is the one that keeps the file small without heroic editing. Because the memory file loads on every single session, everything in it costs context always. The guidance for knowledge that is only relevant sometimes is to put it in a skill instead, a file the agent loads on demand when it judges the task to match. Broad and always true goes in the memory file. Narrow and occasional goes in a skill. So a memory file is how you make one agent smarter about your repository. At a cost measured in context, you pay every time. The next question is what you do when one agent's attention is not enough, when the job needs more reading than a single context window can hold. That is what subagents are for. Chapter 13, Subagents and Delegation. Almost every good practice in agentic coding derives from one fact, and Anthropic's own best practice guidance states it in a single line. The context window fills up fast, and performance degrades as it fills. They call the context window the most important resource to manage. If you internalize nothing else from this course, internalize that. Context is the constraint. Everything else is downstream, which sets up a genuine problem. The work that most needs doing at the start of a task is reading. Where does authentication actually get enforced? Which of these 4 modules owns retries? Is this pattern used anywhere else in the codebase? Answering any one of those honestly means opening 20 files. Those 20 files then sit in the conversation forever, because in an agent loop, the entire conversation is resent on every request. You have spent the majority of your working memory establishing a fact you could have written on a napkin. A subagent is the answer to that. The documentation defines it precisely. Each subagent runs in its own context window with a custom system prompt, specific tool access, and independent permissions. When the main agent hits a task that matches a subagent's description, it delegates, and the subagent works independently and returns results. The parent conversation never sees the 20 files. It sees the paragraph. The economics are the whole point. Anthropic's context engineering guidance describes specialized subagents handling focused tasks with clean context windows and returning condensed summaries, typically on the order of 1,000 to 2,000 tokens, to the main agent. So you spend a large, disposable context to buy back a small, permanent one. It is the same trade as sending a junior engineer down to the archive for the afternoon. You are paying for their whole afternoon. What you get back is the 2 sentences you actually needed, and, crucially, your own afternoon. There are 2 uses that are worth more than all the others combined, and I would teach a beginner these 2 and nothing else. The first is investigation. Anytime the next step is read a lot of things and tell me what you find, that is a subagent. Trace this data flow. Find every caller of this function across the monorepo. Work out whether this library is still used. The output you want is a conclusion and a short list of file paths, not the contents. This pattern is baked deep enough into the tooling that plan mode itself uses it. When the agent explores your codebase before proposing a plan, that exploration is delegated to a dedicated planning subagent, so the exploration output stays in a separate context window. The vendor is doing to itself exactly what I am telling you to do. The second is verification after implementation. Once the work is written, you want something to check it. Doing that check in the same conversation that produced the code is the weakest possible version, and this is where the pattern gets genuinely interesting. The pattern has a name in the official scaling guidance, the writer-reviewer pattern. One context writes the code. A separate, fresh context reviews it, and the stated reason it works is the part I want you to sit with. A fresh context reviews better because it is not biased toward code it just wrote. Stop and consider what that sentence implies. This is not a capability argument. It is not that the reviewer is a better model or has better instructions. It is the same model, with the same weights, reading the same diff. The only difference is that one of them has several thousand tokens of its own reasoning sitting in front of it, explaining why every decision was correct, and the other does not. The one carrying the justification is worse at finding the flaw. That should feel extremely familiar. It is the reason we have code review at all. It is why you cannot proofread your own writing, and why the bug you stared at for 2 hours is found by a colleague in 40 seconds. The machine has the same failure mode, arising from a completely different mechanism, and the same organizational fix works on it. The mechanics are light. In Claude Code, a subagent is a markdown file with a small block of YAML front matter, dropped in a directory in your project or your home directory. Only a name and a description are required. The description is the load-bearing field, because that is what the main agent matches against when deciding whether to delegate. Beyond that, you can restrict which tools it may use, pin it to a specific model, set its permission mode, cap its turns, and give it its own hooks. The stated benefits map onto that list directly. Preserve context, enforce constraints by limiting tools, reuse configurations, specialize behavior, and control costs by routing suitable work to a cheaper model. One mechanical detail has real practical consequences. A subagent receives only its own system prompt plus basic environment details. It does not inherit your conversation. It does not know what you and the main agent have spent the last hour discussing, so the brief you hand it must stand alone. This is the single most common way delegation goes wrong. Someone writes a subagent whose instructions read like the middle of a conversation, and it comes back confidently answering a question nobody asked. Scale the idea sideways and you get parallel work. 2 agents editing the same working tree at the same time is a race condition with extra steps, and it fails exactly the way you would expect. The clean solution is the one you already have in your toolbox: Git worktrees. Each session gets its own checkout of the same repository on its own branch, so file edits cannot collide, and the isolation is enforced by Git rather than by hoping. The tooling supports this directly, including a worktree isolation setting on subagents themselves. If you have ever run 2 long-lived feature branches side by side, you already know how to run 2 agents side by side. The discipline is identical, and so is the merge pain. Now 3 terms that get conflated constantly, and separating them will save you confusion. A subagent is delegation within a single session that reports a summary back to its parent. A background agent is a fully independent session running in parallel, monitored from a dashboard rather than reporting into a conversation. And agent teams are multiple full agent instances that communicate with each other, each holding its own context window. Treat that third one with caution. It is very new, it is disabled by default behind an environment variable, and the documentation notes that teams use roughly 7 times more tokens than standard sessions when teammates run in plan mode. Flag it as experimental, because it is. Which brings me to the honest caveats, and there are 2. The first is cost, and it is my own reasoning rather than a documented finding, though it follows directly from how the loop works. Delegation does not reduce total tokens. It usually increases them. The subagent reads everything the main agent would have read, and then somebody pays to write and read a summary on top. What you are buying is not efficiency, it is cleanliness of the main context, and that is worth paying for right up until it is not. Delegating a task that needs 2 file reads is pure overhead. The second caveat is more important, and it is stated explicitly in the official guidance, which is to its credit. A reviewer prompted to find gaps will usually report some, even when the work is sound, because that is what it was asked to do. Chasing every finding causes overengineering. I want to be very direct about this, because it is the failure mode I see most often in people who have just discovered adversarial review and are delighted with it. You will ask for a critical review. You will get back 11 findings. Perhaps 2 of them are real. The other 9 are a language model doing exactly as instructed by producing plausible criticism, and they will read as reasonable, well-argued, and specific. If you dutifully implement all 11, you will add error handling nobody needs, abstractions nobody asked for, and configuration options nobody will ever set. You will have made the code worse slowly, while feeling extremely rigorous. The defense is scoping. Point the reviewer at correctness and at the stated requirements and say so in the prompt. Does this do what was asked? Does it break anything that currently works? Are there inputs where it is wrong? Not what could be improved, which is an infinite question with an infinite answer. And demand evidence rather than assertions. A failing test, a specific line, a concrete input that breaks it. A finding that cannot produce evidence is a suggestion, and suggestions are optional. Treat the reviewer as a colleague whose taste you respect, but whose findings still have to survive your judgment because you are still the engineer. Delegation buys back context, and a fresh reviewer catches what the writer cannot. But both of those assume you have decided how much the agent is allowed to do on its own in the first place, and how often it stops to ask you. That question, the autonomy dial, is next. Chapter 14, Permissions, Sandboxes, and Autonomy. There is a dial on every coding agent, and where you set it is one of the few genuinely consequential decisions you make. At one end, the agent asks permission before every single action and you approve each one. At the other, it does whatever it decides to do and tells you afterwards. Every real workflow sits somewhere between, and the interesting engineering question is not which end is correct. It is how you choose a point and how you make the point you chose safe. The named settings in Claude Code give you a concrete vocabulary for the spectrum, and the shape generalizes across tools. The default mode, labeled manual, lets the agent read files and requires approval for everything else. Accept edits lets it read and write files and run common file system commands without asking, which is the right setting when you intend to review the diff afterwards. Plan mode lets it read and reason but not touch your source. Auto mode runs everything, with background safety checks by a separate classifier model. Don't task mode runs only pre-approved tools and automatically denies everything else, which is what you want in continuous integration and scripts. And bypass permissions runs everything, full stop. How should you choose? 4 axes, and I would work through them in this order. First, blast radius. What can this agent reach? A container with one repository and no credentials is a different proposition from your laptop with your production, a WS profile sitting in your home directory. Second, reversibility. Is the work in Git on a branch, or is it touching infrastructure and databases where undo does not exist? Third, verification quality. Does this repository have a test suite the agent can run to catch itself? Fourth, your own attention. Are you actually watching, or are you in a meeting with the terminal on a second screen? High blast radius, poor reversibility, weak tests, and divided attention means you turn the dial down. The inverse means you can turn it up, and you probably should. Now the human factor, and this is the part the official guidance states with unusual honesty. After the 10th approval, you are not really reviewing anymore, you are just clicking through. That is not a moral failing. It is how attention works, and every engineer who has ever clicked through a certificate warning or approved a dependency bump without reading it already knows it. The consequence is the important bit, and I want to state it plainly because it inverts most people's intuition. Permission fatigue is itself a security risk. Setting the dial to maximum caution produces a stream of prompts, the stream produces habituation, and habituation produces a reflexive yes on exactly the one prompt that mattered. A wall of approvals is not security theater because the mechanism is fake. It is security theater because the human in the loop stops being a human in the loop. So the practical goal is not more prompts. It is fewer, better prompts. 3 mechanisms get you there, and they are complementary rather than alternative. The first is a classifier. In auto mode, a separate model reviews each non-trivial action before it runs, blocking anything that escalates beyond what you asked for, targets unrecognized infrastructure, or appears to be driven by hostile content the agent read. Two design details are worth knowing. Tool results are stripped from what the classifier sees, so a malicious instruction hidden in a web page the agent fetched cannot address the classifier directly. And entering auto mode drops broad allow rules that grant arbitrary code execution, because a blanket allow anything rule would defeat the point. The documentation's own warning is the correct framing. Auto mode reduces permission prompts, but does not guarantee safety. The second is allow lists. You enumerate specific commands you know are safe in this repository, and those stop asking. This is the cheapest win available, and almost nobody does it on day one. Note one sharp edge. Certain protected paths are never auto-approved regardless of your allow rules, including rights to the Git directory, the agent's own configuration, editor settings, and shell startup files. The safety check runs before your allow rules, not after. That is the correct design, and it will occasionally surprise you. The third is sandboxing, and this is the one that actually changes the security model rather than merely rearranging the questions. The distinction is worth stating carefully because people conflate them constantly. A permission mode decides whether a tool call is allowed to run, judged in advance from the command string. A sandbox constrains what a running process can reach, enforced by the operating system kernel. The sandbox holds regardless of what the model chose to run, and even when an allowed command does more than its name suggests. One is a question, the other is a boundary. Concretely, the built-in sandbox has two independent layers. File system isolation, which by default permits reading widely but writing only inside the working directory and a session temporary directory. And network isolation through an out-of-sandbox proxy, where no domains are pre-allowed and first use of a domain prompts. Underneath, it uses Seatbelt on macOS and Bubble Wrap on Linux and WSL2. Native Windows is not supported. And now the honest limitations, which I want to give you because the documentation itself gives them, and any course that omits them is selling you something. The default file system configuration still allows reading your cloud credentials file and your SSH directory unless you explicitly add credential rules. That is a real footgun, and you should go fix it today. The network proxy allows by client-supplied hostname and does not terminate TLS by default, which means domain fronting can defeat it, and a broad allow of a large host like a code hosting site can itself create a path for data exfiltration. Handing out a Unix socket can mean handing out host access, and the sandbox isolates shell subprocesses only. The file read and write tools go through the permission system instead. The documentation's own summary is the sentence to remember. Sandboxing reduces risk, but is not a complete isolation boundary. There is a formal name for the failure this whole chapter is guarding against, and you should know it because a certification will expect it. The OWASP Top 10 for Large Language Model Applications lists at position LLM06, excessive agency. That is the standard's vocabulary for giving an agent more permission, more tool access, or more autonomy than its task actually requires. The list I verified is the 2025 edition, and given how fast this field moves, you should check whether a newer edition has superseded it. The mitigation is the one you already apply everywhere else in your career: least privilege. Grant the tools the task needs, in the directory the task needs, for the duration the task needs. An agent that only has to read code does not need write access. An agent that only has to run tests does not need network access. Excessive agency is not an exotic AI risk. It is your existing instinct about service accounts applied to a new kind of process. Which brings us to bypass permissions mode, and I will be direct. The documentation says it offers no protection against prompt injection or unintended actions, and that is not hedging, it is a statement of fact. There is a second consequence people miss. In sessions where bypass is available, plan mode's restrictions are not actually enforced either. The agent is merely instructed to plan without editing. Plan mode is a permission mode, not a sandbox, and bypass dissolves it. Is bypass ever defensible? Yes, and I use it. It is defensible when the blast radius is genuinely bounded by something other than the agent's judgment. A disposable container, a virtual machine, a cloud sandbox, a checkout with no credentials in it and no path to production. In that setting, bypass is not recklessness. It is the correct removal of a control that is doing no work. It is indefensible on a developer laptop with live cloud credentials, an authenticated package registry token, and a shell profile the agent can write to. The question is never, do I trust the model? It is, what is the worst thing reachable from this process? Last, checkpointing, because it is the feature people mistake for a safety net. Checkpoints let you rewind the conversation and the code to an earlier state, and they are genuinely useful when a session goes sideways. But the limitation is specific and load-bearing. Checkpoints only track changes made through the agent's file editing tools. They do not track changes made by shell commands or by external processes. So if the agent ran a script that rewrote 50 files, or a migration, or a package install, rewinding restores your conversation and gives you a false sense that it restored your working tree. The official wording is exactly right. This is not a replacement for Git. Git is the real safety net. Commit before you start. Work on a branch. Let the agent make a mess inside a boundary you drew with a tool that has been battle-tested for 20 years. Every autonomy setting in this chapter becomes more defensible the moment there is a clean commit behind you, because the worst case collapses from "I have lost work" to "I have wasted an hour." Set the dial deliberately and give yourself a floor you cannot fall through. Now, with permissions understood, we can settle the terminology argument that everyone in this field gets wrong: the difference between vibe coding and agentic engineering. Chapter 15. Vibe coding versus agentic engineering. These are the two most misused terms in the field, and the confusion between them is not academic. It is why a senior engineer can watch a colleague accept a 1,000-line diff unread, hear it described as the modern way of working, and conclude that this entire discipline is a fashion for people who do not care about software. That conclusion is wrong, but it is a reasonable inference from the vocabulary as it is currently used. So let us fix the vocabulary. Start with the origin, because it is unusually well documented. Andrej Karpathy coined the term on the 2nd of February, 2025. In a post on X, Karpathy is a founding member of OpenAI and formerly led the Autopilot Vision team at Tesla, and he has no coding agent product to sell, which is part of why the field treats his framings as signal. His exact words, and I am quoting them because almost everyone paraphrases them into something more flattering. There's a new kind of coding I call vibe coding, where you fully give in to the vibes, embrace exponentials, and forget that the code even exists. The rest of that post described the practice concretely, and here I am paraphrasing rather than quoting, because the original is not machine fetchable, and I have only verified the substance through secondary reproduction. He described speaking to the tool by voice rather than typing, always clicking accept all, no longer reading diffs, pasting error messages back in with no comment at all, letting the codebase grow past his own comprehension, and working around bugs he could not be bothered to locate. Now the detail almost everyone drops, and it is the load-bearing one. Karpathy explicitly scoped this. His own caveat was that it is not too bad for throwaway weekend projects. The coinage was self-deprecating, and it was fenced. It described a mode of working that is fine precisely because nothing depends on the result. What happened next is the interesting part. The industry stripped the fence off and kept the term. Within months, vibe coding had come to mean any use of an AI to write code at all, including production systems at real companies. Wikipedia's account of the drift notes that roughly a quarter of Y Combinator's winter 2025 cohort were reportedly building this way, and I would treat that as a reported figure rather than a measured one. Karpathy himself has a name for exactly this process: semantic diffusion, where a term is repeated by more and more people until it means less and less. He watched it happen to his own coinage in about a year. Why does the drift matter to you, practically? Because a word that means everything cannot be used to decide anything. If vibe coding means all AI-assisted programming, then you cannot ask, should we vibe code this service, and get a useful answer. And worse, the drift launders an abdication into a methodology. Not reading the code stops sounding like not reading the code and starts sounding like a technique. Simon Willison, co-creator of Django and the most reliable running chronicler this field, has fought that drift directly. Writing on the 19th of March, 2025, in a post titled, "Not all AI-assisted programming is vibe coding, but vibe coding rocks," he stated it flatly. Vibe coding is not the same thing as writing code with the help of large language models. His working definition is one line, and it is the most useful definition available. Building software with a language model without reviewing the code it writes. That is it. The whole distinction sits on one word, reviewing, and his test follows from it. If you reviewed the code, tested it, and can explain it to someone else, that is not vibe coding. That is just responsible software development done with a new tool. Note the title of his post, Vibe Coding Rocks. Willison is not condemning the practice. He is defending the definition on the grounds that a term diluted into meaninglessness destroys its usefulness. And he is right that the narrow version names something real and valuable. Building a one-off script to reshape a CSV, a throwaway internal dashboard, a prototype you will delete on Monday, a small tool to scratch an itch in a language you do not know. Not reading that code is a perfectly rational allocation of your attention. The risk is bounded because nothing depends on it. So you have an operational test you can run on any piece of work in front of you. Did I review this? Did I test it? Could I explain it to a colleague? 3 yeses and the label does not apply. Any no and it does whatever you would prefer to call it. Which brings us to Karpathy's own 2026 framing, and this is the punchline of the chapter. Writing on his blog on the 30th of April, 2026, summarizing a talk, he drew the line himself. His words, "Vibe coding is about raising the floor for everyone in terms of what they can do in software." Raising the floor. That is a precise and generous claim. It means people who could not previously build software can now build some. A teacher automating a spreadsheet, a scientist writing an analysis script, a founder producing a prototype. That is a genuine expansion of who gets to make things, and it is not diminished by being unsuitable for your payment service. Against that he sets agentic engineering, which he characterizes as preserving a professional quality bar while coordinating fallible agents. Hold those two phrases next to each other because the contrast is the whole lesson. Raising the floor, preserving the bar. Those are different objectives. They are not two settings of the same instrument. And the sentence that ties it together, again his own words, "You can outsource your thinking, but you can't outsource your understanding." I would put that on the wall. It is the most compact statement of the discipline I have found anywhere. You may delegate the generation, the search, the mechanical edit, the first draft of the design. You may not delegate knowing what your system does. The moment you no longer understand the thing you are responsible for, you are not supervising, you are hoping. The word he chose was fallible, and he chose it deliberately because the agents are. He illustrates it with a bug from his own project. In an application he built, agents matched users by their Stripe or Google email address rather than by a persistent user identifier. His description of it is the kind of mistake agents still make. Sit with that one for a second because it is beautifully chosen. It is not a syntax error. It is not a crash. It compiles, it passes a casual test, and it works perfectly right up until a user changes their email address or signs in through a different provider, at which point their account quietly detaches from their payments. That is a design-level identity mistake made by a competent-looking piece of work, and it is exactly the class of defect that reading the diff catches and vibes do not. Every experienced engineer listening has shipped a bug of that shape at least once. The difference is that when you shipped it, you understood the code well enough to find it. One honesty note about the other half of the pair. Agentic engineering is emergent vocabulary, not a standardized discipline name. Willison uses it, defining it as building software using coding agents, tools whose defining feature is that they can both generate and execute code, allowing them to test that code and iterate on it independently of turn-by-turn guidance from their human supervisor. Karpathy popularized the contrast in 2026. ThoughtWorks arrives at a similar framing independently. But there is no standards body, no canonical definition, and different authors draw the boundary slightly differently. I am teaching it because it names something real and because the people who name things well in this field converged on it, not because it is ratified. So here is where I want to leave you. Vibe coding and agentic engineering are different disciplines, not points on a single scale. One optimizes for how quickly a person with no relevant skill can produce something that works. The other optimizes for maintaining a professional standard while directing systems that are fast, capable, and wrong often enough to matter. Judging either by the other's objective produces nonsense in both directions. It makes vibe coding look reckless when applied to a weekend script, and it makes agentic engineering look like pointless ceremony when someone is just trying to reshape a spreadsheet. The failure mode to actually watch for is the category error. It is vibe coding a system that has a quality bar and doing it without noticing because the tooling makes both feel identical while you are doing them. The keystrokes are the same, only the review is different, and review is the thing that is invisible when you skip it. This course teaches the second discipline. Everything from here on assumes you intend to remain responsible for the code that carries your name. Which raises the obvious question, and it is the one a skeptical engineer should be asking by now. Does any of this actually make people more productive? The evidence on that is more interesting and considerably less flattering than either the vendors or the critics will tell you. That is next. Chapter 16, what the evidence actually says. Everything so far has been description, what the tools are, what the words mean, how the pieces fit. This chapter is where I show my working, including the parts that cut against me. There is a temptation here to write one of two chapters. One is the hype chapter, where every number comes from a vendor and every vendor number is enormous. The other is the hit piece, where a single uncomfortable study becomes the whole story. Both are cheap, and neither survives contact with an engineer who reads the methods section. So here is the state of the evidence as of August 2026, with the confidence labels left on. Start with the strongest study in the field, which happens to be the one that makes the tools look worst. In July 2025, the research organization METR published a randomized controlled trial by Joel Becker, Nate Rush, Bate Barnes, and David Rain. 16 experienced developers. 246 real issues drawn from their own repositories, bug fixes, features, refactors, not synthetic puzzles. Those repositories were large and mature, averaging around 22,000 GitHub stars and over 1 million lines of code, and each developer had been contributing to them for roughly 5 years. Randomization happened at the level of the individual issue, each one assigned at random to a I allowed or a I not allowed, so every developer was compared against himself. Tasks averaged about 2 hours. The tooling was primarily Cursor Pro, driving Claude 3.5 and 3.7 Sonnet, the frontier models at the time. The headline result, in the author's own words: when developers are allowed to use AI tools, they take 19% longer to complete issues. Look at the interval before you react. It runs from roughly 2% to roughly 39% at 95% confidence. Significant and wide. 16 is a small sample of people, even if 246 tasks is a respectable sample of tasks. Now the part I think matters more than the headline. Before the study, those developers forecast that AI would speed them up by 24%. After the study, after living through the slowdown, task by task, over months, they still believed AI had made them about 20% faster. That is roughly 40 percentage points of error in self-assessment, in the direction that flatters the tool, held by expert practitioners with direct personal experience of the opposite. Economists and machine learning researchers asked to predict the result also forecast large speedups. I want to be precise about what that licenses. It does not license AI makes developers slower. It licenses something narrower and far more useful. Your feeling about whether these tools are helping you is not evidence. It is a vibe. If you want to know, you have to measure. The authors are unusually explicit about their own limits, and it would be dishonest to use their study without repeating them. They state plainly that their work provides no evidence that AI fails to speed up most developers in other settings. No evidence that the result transfers outside a developer's own familiar repositories. No evidence about how future systems will perform, and no evidence that better prompting or scaffolding could not have produced a speedup with those same models. They add that participants typically had only a few dozen hours with the tool, so learning effects are plausible and unmeasured, and that the findings apply mainly to code bases held to very high quality standards. Read that list carefully, and you notice something. The study sampled close to the worst case for AI assistance: maximum human context, maximum quality bar, minimum novelty. A maintainer who has spent 5 years inside a million-line codebase already knows the answer. Then there is the timing, which is the crucial framing. The study ran from February to June 2025. Andrej Karpathy and Simon Willison, independently, both date a real capability step change to November and December 2025. METR measured the generation of tooling that existed before that line. That is not a reason to dismiss the study. It is a reason to date it. And that dating is not me making excuses on METR's behalf. In February 2026, they published a post titled, "We are changing our developer productivity experiment design," and flagged the original results page as out of date. They had run a follow-up trial starting in August 2025. 57 developers, more than 800 tasks, 143 repositories. Returning developers still showed a slowdown of about 18%, but with a confidence interval that now spans 0. Newly recruited developers showed about 4%, also spanning 0. Their own position is that you should not trust even those numbers, because the design broke down. Developers increasingly refuse to participate rather than work without AI, which removes exactly the people who benefit most. Between 30 and 50% reported deliberately withholding the tasks they expected AI to be very good at. And under agentic workflows, developers multitask while the agent runs, which breaks the time measurement itself. Their conclusion, quoted exactly, "Based on conversations with study participants, we believe it is likely that developers are more sped up from AI tools now, in early 2026, compared to our estimates from early 2025. However, because of the selection effects in our experiment, our data is only very weak evidence for the size of this increase." So here is the honest state of play, stated plainly rather than laundered into confidence. There is no rigorous post-inflection replication of that slowdown, not a contradicting one and not a confirming one. The people who produced the famous number tried to produce a newer one and told the world the attempt did not hold up. Anyone quoting 19% slower as a present tense fact today is misrepresenting the source. Anyone telling you the study has been overturned is also misrepresenting it. We do not know, and the professional response to not knowing is to measure locally rather than pick a team. The other controlled studies mostly point the other way, and a fair chapter has to say so. A Google randomized trial of 96 of its own engineers found about 21% faster completion on a complex enterprise task, though the authors call their confidence interval large. QE, Demheirer, Jaff, Musolf, Peng, and Saltz, in management science, ran 3 field experiments across Microsoft, Accenture, and a Fortune 100 manufacturer, 4,867 developers, and found about 26% more completed pull requests, with junior developers gaining most and senior developers least. That last detail is consistent with METR rather than opposed to it. And the study closest to genuine agentic work, On Microsoft's early 2026 rollout of Claude Code and GitHub Copilot CLI across tens of thousands of engineers, found adopters merged roughly 24% more pull requests, sustained over 4 months rather than fading as novelty. That one is not randomized, and its authors caveat it themselves. A merged pull request is not the same as the value it delivers. Notice what all of those measure. Pull requests, tasks, minutes, output, not outcome. None of them tells you whether the software was any good. Which brings me to the numbers I would put on the wall. The Stack Overflow Developer Survey for 2025, with more than 49,000 respondents, found 84% using or planning to use AI tools, up from 76% the year before, and 51% of professional developers using them daily. In the same survey, only 3.1% say they highly trust the accuracy of the output, and 45.7% actively distrust it. Positive sentiment fell from over 70% to 60%. The top frustration, named by 66%, is AI solutions that are almost right, but not quite. And 45.2% say debugging AI-generated code takes longer than writing it themselves. One caveat before you lean on that survey: Stack Overflow's respondent base skews toward people whose traffic these tools have cannibalized, so motivated skepticism is plausible. Say it, then look at the shape of the finding anyway. Adoption went up. Trust went down. That is not a contradiction. It is the signature of a tool that is genuinely useful and genuinely unreliable, precisely the class of thing engineering discipline exists to manage. You already work this way with flaky third-party APIs. You do not stop calling them, you put a check around them. And almost right, but not quite, is the empirical form of an old intuition. Near-miss code costs more than obviously broken code, because broken code fails loudly in development and near-miss code fails quietly in production. Google's DORA research, surveying nearly 5,000 technology professionals in 2025, says the same thing from another angle. It reports a positive relationship between AI adoption and both delivery throughput and product performance. And then, quoting exactly, AI adoption does continue to have a negative relationship with software delivery stability. Their explanation is that acceleration exposes weaknesses downstream. Without strong automated testing, mature version control, and fast feedback loops, more change volume simply means more instability. That is a control systems argument, and it is the most actionable finding in the literature. So let me end where honesty requires. We do not know the sign or the size of the productivity effect for experienced engineers on mature codebases with post-inflection tooling, because nobody has measured it rigorously. We do not know what happens to defect rates in production over time, because no randomized trial assigns AI usage and then follows the software. That study does not exist. And the quality signals we do have, rising duplication, rising churn, rising review load, come largely from vendors who sell the remediation, which does not make them wrong but does mean they cannot carry the argument alone. Even Anthropic's own telemetry, across roughly 400,000 Claude Code sessions, puts verified success for experienced users at around 1 in 3. Any course promising you reliability is lying to you. That is the productivity picture. The security picture is sharper, better understood, and considerably more alarming, and unlike productivity, it does not depend on contested statistics. That is the next chapter. Chapter 17, the Lethal Trifecta. You have been defending against injection attacks your entire career. So let me start with why that instinct is going to mislead you here. Simon Willison coined the term prompt injection in September 2022, deliberately by analogy with SQL injection. The analogy is good for explaining the shape of the problem and dangerous for explaining the fix. We solved SQL injection with parameterized queries and bound variables, and the fix works because the engine has two genuinely separate channels, one for code and one for data. Use them properly, and the attack becomes structurally impossible. A language model has one channel. Your system prompt, the file contents, the web page it fetched, the output of the test run, the description of a tool it might call, all of it arrives as one flat sequence of tokens. There is no bound parameter equivalent. There is no prepared statement for English. Vendors can train models to be more suspicious of instructions arriving inside data, and they have, and it helps. But that is a matter of degree, not of structure. Take the SQL analogy too literally, and you will spend months waiting for a fix that is not coming. Split the problem in two. Direct prompt injection is where the person talking to the model supplies the malicious instruction, jailbreaking, a user attacking their own agent. Indirect prompt injection is where the instruction arrives inside content the agent reads: a web page, a GitHub issue, a code comment, a dependencies readme, the output of a package install, the result of a tool call. That is the one that matters here, and the reason is uncomfortable. A coding agent's entire job is to read large volumes of text other people wrote. It consumes attacker-influenceable tokens as routine operation, by design all day. Which brings us to the most useful mental model anyone has produced for this. In June 2025, Willison published a post called The Lethal Trifecta for AI Agents: Private Data, Untrusted Content, and External Communication. The three legs, in his words, are access to your private data, exposure to untrusted content, and the ability to externally communicate. His claim, quoted exactly, "If your agent combines these three features, an attacker can easily trick it into accessing your private data and sending it to that attacker." His statement of the underlying reason is broader than people expect. Quoting again, "Anytime you ask an LLM system to summarize a web page, read an email, process a document, or even look at an image, there's a chance that the content you are exposing it to might contain additional instructions, which cause it to do something you didn't intend." Any two legs are survivable. An agent holding your secrets with a network connection, reading only content you wrote, is fine. An agent reading the hostile internet with no credentials and no egress is fine. All three at once is an exfiltration machine that has not yet been aimed at anything. Now the part people resist. Willison is explicit that there is no dependable model-level fix. In his words, "We still do not know how to 100% reliably prevent this." He is pointedly skeptical of guardrail products advertising that they catch 95% of attacks, and his reasoning is the reasoning of anyone who has done application security. A 95% filter is not a 95% solution. Adversaries iterate. A defense that fails 5% of the time against a random attacker fails essentially every time against a motivated one, because the motivated one just tries again. Prompt injection mitigation is not a spam filter problem. It is an access control problem, and the defense has to be architectural. Do not let all three legs coexist in one agent run. Read the ability to externally communicate as broadly as you possibly can. It is not just outbound HTTP, it is a GET push, a pull request, a write to a shared file, or a rendered markdown image whose URL encodes the stolen data. In one demonstrated attack against GitHub Copilot Chat, found by Omer Mehrez at Legit Security and rated critical, a hidden injection in pull request comments made the assistant exfiltrate private source code through GitHub's own image proxy, one character per image, every request signed and legal under the content security policy. The channel was inside the trusted platform. Blocking external domains would not have helped. So how do people build the trifecta by accident? Almost always through tools, and increasingly through the Model Context Protocol, MCP, the open standard Anthropic released in November 2024 that lets agents acquire tools from third-party servers. MCP is genuinely useful, and it is also the largest new attack surface in the stack, for a reason that takes one sentence to state and a while to absorb. An MCP server you do not control is an unsigned, mutable extension of your agent's instructions. A tool's description is not documentation. It is text injected verbatim into the model's context every session. Invariant Labs demonstrated this in April 2025 under the name tool poisoning. Malicious instructions written into the description field, invisible in an interface that shows a truncated blurb fully visible to the model. The related attacks have names worth knowing. Rug pull, where a server serves a benign description at approval time and swaps in a malicious one later, because approval is a one-time event and the description is not. Tool shadowing, where one server's description changes how the agent uses another server's tools, trust does not compose. Confused deputy, where the agent is tricked into using one system's credentials on behalf of an attacker who only reach the other. And excessive agency, the formal name for giving one token far more scope than the task needs. There is a benchmark for this. MCP Talks, published in August 2025, tested 45 live MCP servers and 353 real tools, and found an average attack success rate of 36.5%. Its counterintuitive finding is the one to remember. More capable models were often more vulnerable because tool poisoning exploits superior instruction following. Capability does not buy you safety. It buys the attacker compliance. Now picture the accident. On Monday, you add a GitHub MCP server so the agent can read issues, untrusted content, and with a broad access token, private data too. On Tuesday, you add a fetch tool so it can read documentation, more untrusted content, plus an egress channel. On Wednesday, you pointed at your database because you are debugging a data problem. Nobody decided to build an exfiltration machine. It accreted one reasonable convenience at a time, and no single step looked like a security decision. Map this onto the standards vocabulary, because a certification-level engineer should speak both. OWASP publishes a top 10 for large language model applications. The edition I can cite is the 2025 one, and you should check whether a newer one has landed by the time you hear this. 4 entries carry most of the weight for agentic coding. LLM01 is prompt injection. LLM02 is sensitive information disclosure. LLM03 is supply chain. And LLM06 is excessive agency, the formal name for I gave the agent too many permissions. The trifecta is the mechanism. OWASP is the taxonomy. Now the practical part. Before an agent run, decide which leg you are breaking and say it out loud. Remove egress, no network tools, no auto-fetching of URLs, a sandbox with no outbound route. That is the cheapest leg to break and the one people give away first. Or remove the private data, run against a scratch clone with dummy credentials, never mount a real environment file, and scope tokens hard, fine-grained, per repository, read-only wherever the task allows. The GitHub exfiltration proof of concept only worked because the token could read private repositories at all. Or remove the untrusted content, pin the agent to a curated context, and do not let it browse. That is the leg you will least want to give up, which tells you why this problem persists. Then a handful of controls that cost almost nothing. Pin MCP server versions. Invoking a server at latest from a config file is a standing invitation to a rug pull. Read tool descriptions as code, not documentation, and prefer servers whose source you can read. Treat approval as per configuration hash rather than per server, so any change forces reapproval. That is the fix cursor shipped after a rug pull vulnerability was disclosed against it. And treat your agent configuration files as security-sensitive assets. Version them, diff them, alert on unexpected changes. The self-replicating NPM worm tracked as Shai-Hulud injected rogue MCP servers straight into local assistant configuration files, establishing persistence inside the developer's agent rather than the operating system. Almost nobody watches those files. 2 closing points I want to land harder than the rest. The first, instructions in the prompt are not a control. In the widely reported Replit incident of July 2025, a user declared a code freeze, told the agent in capital letters not to touch production, and the agent deleted a live production database anyway. The engineering lesson is exact. I told it not to is not an access control mechanism. Only the absence of the credential is. The second, your convenience flags are an attacker's capability. In the NX supply chain compromise of August 2025, the malicious install script searched the machine for installed AI command line tools, Claude Code, Gemini CLI, Amazon Q, and invoked them with their permission bypass flags, telling them to enumerate the file system for secrets and wallet files. An installed agent with a documented bypass flag is a pre-credentialed, file system traversing implant waiting for someone else to type the flag. That reframes, I skip permissions, because it is faster from a personal risk decision into a supply chain exposure. This chapter is a primer. The mechanism, the taxonomy, and the architectural rule, which is enough to stop you assembling the trifecta by accident in your first month. Part 3 goes deeper. The full MCP threat model, the published vulnerability record, hallucinated dependency attacks, and sandboxing patterns. Next, though, a different kind of misleading signal, the numbers everyone quotes when choosing a model, and why leaderboard position is a poor basis for a purchase decision. Chapter 18, Benchmarks and Why They Mislead. Every model announcement leads with a number. You will be handed those numbers by vendors, by colleagues, and by whoever is arguing for a particular tool in your team channel. So you need to know what those numbers measure, what they cannot measure, and why leaderboard position is one of the weaker inputs to a purchase decision. Start with what the main coding benchmarks actually are, because they are better designed than the cynical read suggests. SWE Bench, from Princeton and LP, is described by its own documentation as a benchmark for evaluating large language models on real-world software issues collected from GitHub. The paper was accepted to the 2024 International Conference on Learning Representations as an oral. The task format is elegant. You get a repository at a particular commit and a real GitHub issue, you produce a patch, and you are graded by running the repository's own unit tests. The reference solution is what the real pull request actually did. That is a genuinely real-world evaluation shape, and it is why the benchmark became the standard. The number people quote is not plain SWE Bench, though. It is SWE Bench Verified, a subset of 500 samples released in August 2024, described as 500 engineer-confirmed solvable problems. It exists because a large fraction of the original tasks turned out to be unsolvable or underspecified, broken tests, missing information in the issue text. Scores on the original set therefore understated capability. Verified is the de facto standard number in model announcements. There is a harder successor, SWE Bench Pro, from Scale AI. 731 instances across 11 repository classes and 4 programming language categories, described as an enterprise-level dataset for testing agent ability on long-horizon software engineering tasks. And there is Terminal Bench, which is where the field went once agents got the ability to run commands. Its own description is a collection of Harbor-native benchmarks to help agent makers quantify their agent's terminal mastery, and it is presented as a Stanford and Claude collaboration. It scores agents on real terminal work, building Linux kernels, configuring Git servers, training models, sysadmin tasks. Terminal Bench does one thing that I want you to notice, because it is the most honest design decision on any of these leaderboards. It reports agent and model pairs, not models alone. As of the 3rd of August 2026, the top of the version 2.1 leaderboard read: Claude Code paired with Fable 5 at 83.8%, plus or minus 1.2. Codex paired with GPT 5.5 at 83.1%, plus or minus 1.1. And Terminus 2 paired with Fable 5 at 80.4%. 17 entries, spanning roughly 58.7% to 83.8%. Those numbers will have moved by the time you hear this, which is exactly why I have dated them. The pairing matters. Terminal Bench is conceding in its data model that the harness is part of the system under test. The harness is everything wrapped around the model, the loop, the tools, the prompts, the context management. The same model in 2 different harnesses is, for practical purposes, 2 different products. Now, 5 reasons those numbers will mislead you. The first is contamination. A paper titled The SWE Bench Illusion, When State-of-the-Art LLMs Remember Instead of Reason, by Shanchao Liang, Spandon Garg, and Roshanak Zylaukian Moghaddam, states that performance gains on SWE Bench Verified may be partially driven by memorization rather than genuine problem-solving. Their diagnostic is clean, and I like it a lot. They asked models to identify the buggy file path from the issue text alone, no repository access, no code. On benchmark repositories, the models were right 76% of the time. On repositories outside the benchmark, 53%. That gap is not reasoning. Public benchmarks built from public GitHub history are in the training data by construction, and there is no way around that except building new benchmarks faster than models are trained. The second is the harness confound, which I have already named but which deserves to be stated as a warning. When a press release gives you a SWE Bench verified score, it usually does not tell you what scaffold produced it. Same model, different loop, different number. If you are comparing two models using two different harnesses, you are not comparing models. The third is distribution mismatch, and this is the one that should decide the argument for you. SWE Bench is single repository, Python dominant, and shaped as issue in, patch out with a ready-made Oracle. The tests that came with the real fix. Now describe your work. Your code base is polyglot. There is no Oracle waiting for the change you are about to make. And the issue is not a well-written GitHub ticket, it is 3 messages in a Slack thread, one of which contains the actual requirement and 2 of which contradict it. The benchmark tests a task shape you rarely encounter. The fourth is selection and reporting effects. Vendors report their best configuration. That can mean a custom scaffold, best-of-end sampling, or a filtered subset. Error bars, and Terminal Bench does publish them, almost never survive into the marketing. When two systems are 1 point apart, and the interval is plus or minus 1.2, you are looking at a tie being sold as a win. The fifth is that benchmarks saturate and get gamed. The progression from SWE Bench to Verified to Pro and Terminal Bench from 1.0 to 2.1 is exactly that treadmill. A benchmark's useful life ends when everyone is optimizing against it. And underneath all 5 sits a deeper problem that no benchmark design solves. Passing a test is not the same as being correct. It is not the same as being maintainable or idiomatic for your codebase or something a reviewer would approve. Andrej Karpathy put this better than I can in his June 2025 talk at the YCAI Startup School. Demo is works.any, product is works.all. A benchmark is a demo. It measures whether the thing worked at least once on a task that had a known answer under conditions someone else chose. So here is the practical rule I would put in your head, and it is the one the research supports. Benchmarks tell you which models are worth trying. They tell you nothing about whether an agent will work on your codebase. Only your own evaluation does that. Which brings me to the constructive half of this chapter, and to a skill I would consider genuinely certification level. You should build your own eval. An eval is just a test suite for a non-deterministic system. You cannot assert equality on a model's output, so instead you define a set of tasks, run the system, score the results, and report a rate. It has 4 parts: a dataset of tasks, a runner, a grader, and a metric. Here is how to build one for your repository in an afternoon. Take 10 to 20 issues that your team actually closed in the last quarter. Real ones, spanning the mix you really do, a couple of bug fixes, a small feature, a refactor across 3 files, a dependency upgrade, and at least one thing that requires understanding a convention nobody wrote down. For each, check out the repository at the commit just before the real fix landed. Your grader already exists, and this is the part people miss. The tests that shipped with the real fix are your Oracle. Add your linter, your type checker, and your build. That is a deterministic scoring function you already own and already trust. Run each task 3 to 5 times, not once. These systems are non-deterministic, so a single run tells you almost nothing. Report pass rate, and record 2 other things everybody forgets: wall clock time and token cost. A model that resolves 5% more tasks at triple the cost is a different decision than the leaderboard implies. Change one variable at a time. If you are comparing models, hold the harness fixed. If you are comparing harnesses, hold the model fixed. Otherwise, you have reproduced the exact confound you were warned about. And add one human judgment to the automated score, because the automated score is not sufficient. For each result, mark it. Would you merge this as it stands? Would you merge it after a small edit? Or would you throw it away? That three-way split is closer to value than any pass rate, and it takes seconds per task. 2 warnings. Your eval will leak. Once you have tuned your prompts and your memory files against those 20 tasks, they stop being a fair test, so refresh a portion of them every quarter, the same way you would rotate a holdout set. And keep it small enough that you will actually run it. An eval you run monthly beats a rigorous one you build once and abandon. The payoff is that you get to make claims nobody can argue with. Not this model tops the leaderboard, but on our repository, on 20 of our own tasks, this configuration produced a mergeable change 60% of the time at this cost, and the other one managed 40%. That sentence is worth more than every benchmark score published this year, and you are the only person who can produce it. You now know what to buy on and what to ignore. Next, what to actually do on Monday morning. Chapter 19, your first week. This chapter is a set of instructions. If you do nothing else from this course, do these things in this order, because the order is not arbitrary. Each habit makes the next one cheaper. Start with the single highest leverage practice, and it is not a prompting trick. Give the agent a way to verify its own work. Here is the mechanism, stated plainly in Anthropic's own guidance for Claude Code. The agent stops when the work looks done. Without a check it can run for itself, looks done is the only signal available to it, and you become the verification loop. Sit with that. If the agent cannot tell whether it succeeded, then the only thing standing between a plausible-looking diff and your main branch is your attention, applied at the end of a long session, to code you did not write. That is the worst possible place to put a human. So before you ask an agent for anything on day 1, spend 20 minutes making sure a check exists and that the agent knows how to run it. A test suite is the obvious one. A build that exits non-zero is a check. A linter is a check. A type checker is a check. A diff against a known good fixture is a check. For anything visual, a screenshot comparison is a check. Verify the command works from a cold checkout yourself, then tell the agent exactly what it is. There is an escalation ladder here, and it is worth knowing all 4 rungs even if you only use the first this week. The weakest is an instruction in your prompt telling the agent to run the tests, advisory, and it will sometimes skip it. Stronger is a session-level goal condition that gets rechecked every turn. Stronger still is a hook, deterministic code that runs when the agent tries to end its turn and blocks it if the check fails. Strongest is a separate verification subagent, a fresh context with a clean view, asked to confirm the work independently, which works better than self-review for the same reason a second pair of eyes works better in code review. It is not biased toward the code it just wrote. And from your very first session, adopt one verbal habit. Ask for evidence, not assertions. When the agent says, "I fixed the failing test," the correct response is not "great." It is, "show me the test output." An agent that says it ran the tests and an agent that pastes the passing output are 2 different levels of trust, and the distinction costs you nothing to enforce. Second habit, explore, plan, implement, commit. Have the agent read before it writes. Most harnesses have an explicit planning mode where the agent can read and reason but cannot edit. Use it. Ask for a written plan, which files, what change in each, what could break, read the plan, correct the plan, and only then let it implement. Correcting a plan costs 1 paragraph. Correcting an implementation costs a session. But note the caveat, because this is where new users overcorrect. Planning has overhead. The official guidance is blunt about it. If you could describe the diff in 1 sentence, skip the plan. Planning pays when the approach is genuinely uncertain, when the change spans several files, or when the code is unfamiliar to you. For rename this function and update the callers. A plan is ceremony. Third, write a short memory file. Your project's memory file, Claude, MD, agents. MD, whatever your tool calls it, is a plain markdown file in the repository that gets loaded into context every single session. It is standing orders. And the mistake almost everyone makes in week 1 is writing too much. The test for every line is exactly this. Would removing this line cause the agent to make a mistake? If not, cut it. This is not aesthetic advice. Bloated memory files cause the agent to ignore your actual instructions because everything in that file competes for attention with everything else, and a 200-line file of platitudes buries the 3 lines that mattered. So what earns a place? Commands the agent cannot guess, how to run your tests, your dev server, your migrations, style rules that differ from the language's defaults, repository etiquette, branch naming, commit conventions, what must never be committed, architectural decisions that are not visible from any single file, environment quirks and non-obvious gotchas, the kind of thing you would tell a new hire in their first week, and that would take them a month to discover alone. And what does not? Anything derivable by reading the code. Standard conventions the model already knows, detailed a PI documentation, facts that change frequently, which will simply rot. Start at 10 to 15 lines. Grow it only when you catch yourself making the same correction twice. 2 diagnostics for later. If a rule keeps being ignored, your file is probably too long, not too quiet. If the agent asks you something the file already answers, the phrasing is ambiguous. Fourth, context hygiene. The context window is the working memory of the session, and it is a finite resource that degrades as it fills. 2 practical consequences for week 1. Clear it between unrelated tasks. Starting a fresh session costs you nothing, and carrying a dead conversation costs you accuracy. And learn this rule, which is the most useful single line in the whole practice literature. If you have corrected the agent more than twice on the same issue in one session, stop. The context is now cluttered with failed approaches, and every one of those failures is still sitting there being read as an example on every subsequent turn. Do not correct a third time. Clear the session and start again with a better prompt that includes what you learned. Your third correction is being weighed against 2 demonstrations of the wrong approach, and you will lose that argument. 2 related mechanics worth knowing on day 1. Interrupting the agent mid-action preserves your context, so interrupt early rather than watching it go the wrong way politely. And most tools have a rewind that restores both the conversation and the code to an earlier point, but be careful, because those checkpoints typically only track changes made through the file editing tools, not changes made by shell commands or external processes. It is not a replacement for Git. Fifth, know the named failure patterns, because you will hit at least 3 of them this week. The names come from Anthropic's published guidance. The gloss is mine. The kitchen sink session. 1 conversation carrying 4 unrelated tasks, growing slowly worse at all of them. Fix. 1 session, 1 concern. Correcting over and over, covered above. 2 strikes, then reset. The over-specified instruction file. Someone writes 300 lines of rules and then complains the agent ignores them. It is ignoring them because you buried them. The trust then verify gap. You review the first 3 diffs carefully, they are all fine, you relax, and the one you skim is the one with the subtle authorization bug. This one is a genuine cognitive trap, not a discipline failure, which is exactly why the answer is an automated gate rather than a promise to yourself to concentrate harder. Infinite exploration. The agent reads 40 files looking for something that was never there, burning context and time. Give it a budget and a starting point. Sixth, and this is the safety net under everything else, small diffs and hard Git discipline. Commit before you start, so you always have a clean point to return to. Work on a branch. Commit at every green state, not at the end. Keep changes small enough that you can actually read the diff, and read the diff every time in week 1 especially, because that is how you build the calibration to know later which kinds of work this thing is reliable at. One honest warning about permissions. The official documentation makes a point I would have made anyway. After about the 10th approval prompt, you are not really reviewing anymore, you are clicking through. Habituation is the enemy. The answer is not to be more diligent. It is to reduce the number of decisions by allow-listing the genuinely safe commands and sandboxing the rest, so that when a prompt does appear, it is rare enough to deserve your attention. That is the whole first week. Give it a check it can run. Plan when it matters and skip the plan when it does not. 15 lines of memory, clear the session. 2 corrections, then reset. Small commits you actually read. None of this is exotic. It is version control, code review, CI gates, and onboarding a new colleague applied to a colleague who is fast, tireless, occasionally confidently wrong, and has no memory of yesterday. 1 chapter left. In it, I will give you my actual verdict on all of this, state it as an opinion rather than a finding, and then tell you exactly what evidence would prove me wrong. Chapter 20, Verdict and what would falsify it. Everything up to now has been an attempt to describe the field fairly. This chapter is my opinion, labeled as opinion, and then, because an opinion you cannot test is just a mood, the specific things that would prove me wrong. Here is the verdict in 5 claims. The first claim, the capability change is real, and it is recently dated. 2 credible independent observers, neither of whom sells a coding agent, put a step change in November and December of 2025. Andrej Karpathy, writing in February 2026, said this, verbatim. It is hard to communicate how much programming has changed due to AI in the last 2 months. Not gradually and over time in the progress as usual way, but specifically this last December. There are a number of asterisks, but IMO coding agents basically didn't work before December and basically work since. This is the same man who, in October 2025, was telling a podcast audience that agents were cognitively inadequate and that this would be the decade of agents rather than the year of them. Simon Willison, independently and from a different vantage point, named a November 2025 inflection. That is not one enthusiast. That is 2 careful people, with different datasets and a track record of skepticism, converging on the same quarter. My opinion is that they are right, and that this is why a genuinely excellent engineer can be fluent in software and illiterate in this. The ground moved recently. You did not fall behind. The second claim, the vocabulary is mostly simple ideas wearing intimidating names. Context engineering is deciding what goes in the window. A harness is everything wrapped around the model, the loop, the tools, the prompts, the permissions, and it is most of the product. The model context protocol is a wire format, so every tool stops writing the same adapter. Skills are progressive disclosure. Subagents are separation of concerns applied to a context window. An agent, in Willison's definition, is a system that can generate code, execute it, and iterate on it without turn-by-turn supervision. None of this would have surprised you if it had arrived with boring names. You were behind on a glossary, not on engineering. The third claim, the binding constraint is context, not intelligence. This is the one I would defend hardest because it explains the most. Anthropic's own engineering writing states it directly. As the number of tokens in the context window increases, the model's ability to accurately recall information from that context decreases and gives the reason. Attention requires every token to relate to every other token, which is n-squared pairwise relationships. That single fact generates almost every practice worth having. It is why memory files must be short, why you clear between tasks, why subagents exist, and why just paste the whole repository in does not work and will not start working simply because windows get bigger. When people say a model is stupid, they are usually describing a saturated context. The fourth claim, verification is the whole discipline, not prompting. Verification. 66% of developers in the Stack Overflow 2025 survey name solutions that are almost right, but not quite, as their top frustration, and 45.2% say debugging generated code takes longer than writing it themselves. Google's DORA research finds AI adoption associated with higher throughput and lower delivery stability. METR found experienced developers slowed by 19% while believing they were sped up by 20%. All of it points the same way. Generation got cheap and checking did not, so checking is where the work now is. Give the agent an oracle it can run, or you become the oracle. The fifth claim, and the one I hold most firmly: the engineer's judgment became more valuable, not less. Willison's framing is that writing code is cheap now, the cost of producing initial working code has fallen to almost nothing, and the scarce resources are therefore review, verification, and judgment. Karpathy's version is sharper. You can outsource your thinking, but you cannot outsource your understanding. If code is cheap and review is expensive, the person who can look at a plausible diff and know it is subtly wrong holds the scarce skill. That is you. Your 10 years did not depreciate. They repriced upward and moved to a different part of the workflow. That is the thesis. Now the part that makes it worth anything: what would falsify it? Start with the first claim, the capability step change. Because it is the most exposed, it rests substantially on the testimony of 2 practitioners. A rigorous post-inflection randomized controlled trial with developer-level randomization, genuinely agentic tooling, real issues on real mature repositories, and the selection effects that broke METR's follow-up design properly controlled that still found experienced developers measurably slowed would falsify it. Not weaken it, falsify it. It would mean the step change was largely perceptual, and given the 40-point gap between how fast developers feel and how fast they are, that is not far-fetched. I would update hard and say so. A softer version of the same test. If adoption keeps rising while trust and sentiment keep falling for another 2 survey cycles, the improvements are not reaching practitioners the way the inflection narrative implies. Sentiment already fell from over 70% to 60% in a single year. If it keeps sliding while the models keep improving, my story is wrong somewhere. Now the third claim, that context is the binding constraint. This one has a clean signature. If an architecture arrives where recall does not degrade as the window fills, demonstrated on long horizon tasks, with performance flat as a function of context length rather than sloping downward, then most of the harness discipline in this course becomes historical trivia within a year. I do not expect that, but I am not confident enough to bet against it, and it is worth watching precisely because it would obsolete so much at once. The fourth and fifth claims are about quality and judgment, so falsifying them needs longitudinal evidence about what happens to code after it is merged. Here is the honest position. The evidence we currently have: rising duplication, rising churn, falling refactoring activity, rising review times, comes overwhelmingly from vendors who sell the remediation for exactly those problems. That is a real conflict of interest, and it means those figures cannot carry the argument alone. So the test runs in both directions. If independent, non-vendor longitudinal measurement showed codebases built this way degrading measurably over time, sustained rises in defect escape rate, in time to change, in maintenance cost, controlled against comparable codebases, my emphasis on verification would be vindicated more strongly than I have argued it. But if independent measurement showed those signals converging back to baseline as tooling matures, then I have overweighted verification, and the answer was simply to wait for better models. And the sharpest falsifier for the fifth claim: if review itself becomes reliably automatable to a standard humans accept, if adversarial review agents can be shown, on held-out defect sets, to catch the classes of defect-experienced human reviewers catch, then judgment stops being the scarce resource, and my central claim about where value moved is wrong. That has to be measured on a proper holdout, because a reviewer prompted to find problems will report problems whether or not they exist. But if someone demonstrates it, I lose the argument. One more, and it is uncomfortable for me. Anthropic's own telemetry across roughly 400,000 coding sessions puts verified success, the goal met, with a commit or passing tests to prove it, at around 1 in 3 for experienced users. If that is still 1 in 3 in 2 years, the capability compounding I am implying is not happening. Now let me give the strongest objection its due, because I do not have a clean answer to it. The strongest case against this thesis is that the capability narrative rests on practitioner testimony, and the most robust finding in the field is that practitioner testimony about AI productivity is unreliable. METR's developers lived through a 19% slowdown and reported a 20% speedup. Karpathy and Willison are practitioners, subject to the same failure mode as everyone else, and noting that they are unusually careful is not a rebuttal. The METR participants were unusually careful too, and were still wrong by 40 percentage points about their own experience. My partial answer is that their claim is about capability rather than their own productivity. The agent can now complete long, multi-step tasks without falling apart is more checkable than I am faster, and anyone running the tools can observe it independently. But that is a partial answer, not a decisive one. The strongest evidence for my position is weaker than the strongest evidence against it, and the only clean response is the one I have been recommending for 20 chapters. Measure it yourself, on your own repository, with your own tasks. There is one place I will not move. The security architecture holds regardless of who is right about productivity. If there is no dependable model-level fix for prompt injection, and the people closest to it say there is not, then the Lethal Trifecta discipline is correct whether these tools make you 30% faster or 20% slower. Private data, untrusted content, external communication. Never all three in one agent. That conclusion does not depend on the capability debate at all, which is a useful property in a field where almost everything else does. That is the end of part 1. You have the vocabulary, the mental model, the evidence and its limits, the security architecture, and a first week you can execute on Monday. Part 2 is the practice. A full comparative teardown of the tools and models, what each harness does differently, how the pricing shapes behave, where the open-weight options genuinely compete, plus the daily craft, including test-driven development with an agent, parallel sessions, migrations, and debugging. Part 3 is mastery. Security in depth, building real evaluations, the economics of tokens, governance and team adoption, and the parts of this that remain genuinely unresolved. A last word. I have not tried to tell you what to think, because you are perfectly capable of deciding for yourself, and you have a decade of judgment that none of this obsoletes. What you were missing was a vocabulary and a map, and you now have both. What you already had, the instinct that says a plausible-looking change is wrong before you can say why, turns out to be the part that is hard to replace. Use it.